Okay, yep, seems to be working on the audio. And presumably I'm streaming. Okay, wonderful. Okay, so, oh, I should probably also change the title. Go to my channel. I'm live, wonderful. How do I change the title? Manage stream. Okay, I can see the title, but can I edit? Yes, okay. Cool. String diagrams. All right. So the point of this stream is that someone posted recently, if I search in the right box, about these string diagrams. They made a MATLAB branch. If you click here, you can see that you can see this little string diagram. And I got pretty excited about this because for a while I've been interested in this paper, Categorical. It's either something about composable crypto. This one, which is this like categorical theoretic treatment of composable cryptography. And they had this cool proof, this sort of pictorial proof of the security of the one-time pad, which is here. Basically, they carry out this proof using these diagrams, and they describe what sort of diagram transformations are allowed. And this is basically a demonstration that category theory can be used to like visualize proofs in cryptography, which I thought was sort of cool. And now that string diagrams have been introduced in this post here, I thought I would try and see if I could implement the stuff from this paper. Now, I don't really know anything about category theory or how it's supposed to be implemented here. So basically this could be me doing some learning and potentially not getting very far, but I thought it would be fun to try anyway. So I think the first thing I need to do is go to the branch that this person has indicated. Yuma Mizuno string is the name of the branch. Okay, let's do that. So let's go to Yuma Mizuno string. Okay. Sorry, type it right. Of course, the string is not showing up. The reason it's not showing up is presumably because I need to do some kind of get operation. Get fetch sometimes fixes this. Has it fixed it? Let's see. Yuma Mizuno string. Two days ago was when this was last committed to. Presume, okay, maybe I need to like synchronize or something. Okay, there it is. Great, so now I'm here. And if I look at this, wonderful, there's a draft pull request for it. Okay, so if I look at this pull request, I can see that there are 7 files changed. So maybe it would be helpful to go and look at what files those are, so to try to understand what's going on. Okay, so there's MATLAB tactic widget string diagram.lean. So let's search for that. And here, imports are out of date and must be rebuilt. So let's do that. Let's also boot up the info view. See how many. Looks like we're only a few files away from compiling this. So basically, what do we have here? We have a structure called atom1. It consists of expressions, and then morphisms. Expression for 1 morphisms. Yes, so a morphism in category theory, as I recall, in category theory, we have these objects and we have these morphisms. And it's sort of like a generalized notion of a monoid where you can compose the morphisms, and there are always these identity morphisms. And so what this is sort of indicating to me is that, for any expression, we have the identity morphism on that expression. So what I'm sort of sensing is that we're about to make a category out of these atoms. And it's going to probably be, this is probably what they would call like a free category or something, where basically you can have the identity morphisms and the composition morphisms, and this third of morphism, which I have no idea what that is supposed to be. But we define some other functions here. Wonderful, we're compiling. More1.e, which takes a morphism to a meta-m expression. Monoidal category struct tensor unit. Morphism 1 to list. Structural atom. Lots of different things. Let's see if we can find the point in the code where this diagram was generated, and see if we can start like modifying things from there. So does it say the name of the file which produced this? I wonder if I will like see. So let me like open up all the files here. So it's not going to be this. This is just mathlib.lean, and this is mathlib/tactic. These are just files that import a bunch of things and don't do anything else. We also have a nolint file. That's fine. This file we already added. Let's also open up this file. Yang Baxter. Imports are out of date. Okay, let's restart this file. And are there any other files? Widget, penrose, monoidal.dsl. What the heck? Let's just open up all of the files that seem to be containing interesting code. I think these are all the files. This one, and then finally this one. So this is a .style file. .sty. This is usually, that's interesting. This is like a tech file. And presumably the point is that this is what is used to like generate the diagram. Like goes through LaTeX. That's interesting. And presumably this is also some file format from the tech environment. Okay, a string diagram.lean. With panel widgets, you can use shift-click to select expressions in the goal. Shift-click. 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 Ooh, okay. I just activated the string diagram. That's fun. Okay. So what is it saying? We have G. We have F arrow G tensor Y, X tensor Y. F arrow X tensor Y equals G. So G what do we got here? What is the Yang-Baxter lemma? Is this something that I should know about if I were a category theorist? Yang-Baxter equation, or star triangle relation. It's a consistency equation first introduced in the field of statistical mechanics. It depends, yeah, looking like category theory over here. Depends on the idea that in some scattering situations, particles may preserve their momentum while changing their quantum internal states. Entering into like quantum systems. This is fun. Yeah, a lot of the like category, for some reason, a lot of the categorical cryptography people are also interested in quantum, which is interesting. Presumably it's like, models it well or something. R inverse hat, what is this inverse hat? R inverse hat tensor 1 and 1 tensor R inverse hat. And R inverse hat tensor 1 is equal to 1 tensor R inverse hat times R inverse hat tensor 1 times 1 tensor R inverse hat. Matrix R acting on 2 out of 3 objects satisfies this. In one-dimensional quantum systems, R is the scattering matrix. If it satisfies the Yang-Baxter equation, the system is integrable. The Yang-Baxter equation also shows up when discussing knot theory and braid groups, where R corresponds to swapping 2 strands. Since one can swap 3 strands in 2 different ways, the Yang-Baxter equation enforces that both paths are the same. Illustration of the Yang-Baxter equation. Right. So we have this diagram here. Presumably this is something that might be called a string diagram. Whisker right tensor. Okay. Okay, I want to do this shift clicking to like see the string diagram. How do I see the string diagram? What was it that like allowed me to see the string diagram before? Ah, ha ha ha! Okay, we've achieved the string diagram from Wikipedia. Wonderful. Okay. For promotion, okay, I'm getting a weird chat in my... Oh wow, somebody is offering to like sell me chatbots. That's wonderful. Okay. So this is wait. So we're about to achieve one side of the Yang-Baxter equation, which has the string going down one side. And now presumably if I click on the other side, it will now show me the other side of the Yang-Baxter equation. Wonderful. Okay. We're learning about the Yang-Baxter equation, namely that it is... We have learned that we can move a string from one side of the diagram to the other side of the diagram, which is a nice learning for us. Okay. So you've achieved the moving of this string. Excellent. So that's the Yang-Baxter equation. And presumably this is helpful somehow. Well, I don't necessarily see how it's helpful because in these examples, I don't see any like reference to the Yang-Baxter lemma. But presumably if we like look carefully at all of this notation, we should be able to understand what has happened. Exact w.lim. With panel widget selection panel. So what is this? Okay, let me like see. This is maybe what is being done within the tactic mode to like activate the like visibility of the string diagrams. So with panel widget selection panel. With panel widgets, display the selected panel widgets in the nested tactic script. For example, assuming we have written a geometry display component, by with panel widgets geometry display, simp ruffle will show the geometry display alongside the usual tactic state throughout the proof. And so instead of geometry display, we have selection panel, which is presumably something else that has been written here. No, apparently not. Selection panel.lean is somewhere in the proof widgets package, which is a lake package. Component panel widget props. Okay, so this is just something that helps you display. Okay, that doesn't it. But it's whatever it is what Yuma Mizuno has been using to make these nice visualizations available to us. Okay, so exact w.alim, false.alim. W is false, exact w.alim. Okay, so this is just a okay, this is a little weird. This is just a trivial proof. Is this so that maybe this is like a sorry? This is the equivalent of sorry. Basically what they put here. Okay, I'm observing now that there is false in the there's false in the statement of this lemma, which suggests to me that which makes it very easy to prove a lemma when false is one of the hypotheses. So presumably what they've done here is they have put this here so that they don't have to actually prove these lemmas, which are presumably like very complicated categorical theoretical lemmas that require hundreds of lines of category theory proof in order to actually prove them. Instead, just so that we can see these things, they've put this like false lemma so that it's basically the equivalent of sorry, but without like using sorry. Yeah, okay, very fine. And okay, so like let's shift click this and see. So this is the string diagram. Aha, we found the string diagram that they produced here. This is this string diagram, clearly. All right, very cool. Yes. And this, okay, so this is that string diagram. This is this string diagram. And presumably, okay, so this is something that is being proved equivalent to something else. So if I understand correctly how category theory, how like these string diagrams work. So this is something that's pointed out here. Let me venture a conjecture for what is about to happen when I select the other side of this equation. If I go to the cryptography paper that was introducing all these string diagrams, one of the things that I think was noted, we'll see if it was noted. If it's not noted here, it's also noted on this other guy's blog who blogs about using string diagrams for category theory. I don't necessarily see it here. Let me see if I can find it. Let me see if I can find it on that. So there's this person, Chrono Kirby, who blogs, posts a sketch of synthetic, yeah, and so this, so he has written like this extended blog post about these string diagrams for cryptography as well. And he has like these. So like this is what I expect is about to happen. There is this observation that if you have this string diagram that like goes up and then back again, that's equivalent to just a straight line. So what I suspect might happen here if I click on the other side is that it'll just look like either a straight line or it'll be sort of wrapped around but the other way. It'll just be another like line like this, but it'll be wrapped around in some other way. So let's see if that is what happens. Shift click. No two morphisms. Okay. It's telling me that there's no two morphisms. So maybe what's happening here is that there's no two morphisms, like because it's a straight line, it thinks that there's no string diagrams to show. Sorry, I just want to make sure. This, if I shift click, this is what I get from that. And when I shift click here, there's no two morphisms, so it doesn't want to show me that. Interesting. Monoidal category C. C is of some type. Monoidal category. Yeah, very interesting. Okay. So I don't know exactly what's going on. Let me see if I can like try and parse out how let me see if I can try and parse out how the written out with all the like arrows and stuff, how the written out lean string translates to these diagrams. But first, let me. Someone is offering to like bot my channel. Surely this is against the Twitch rules. Can I ban them? I don't know. I don't know. Unfortunately, I don't know how to ban people. So, anyway. Yes. So what this is, so when I select this left hand, the expression on the left hand side of the equality here, I get this diagram. What exactly is this diagram? Okay, so we have eta and we have epsilon. And eta, what is eta and what is epsilon? This is x, this is x, this is x, this is x. So eta, what is this tensor unit? So eta, I think the way to interpret, sorry, let me get the string diagram back just a second. For this, I want to shift click on this. Eta is something that takes in this x and this epsilon. So the left. I'm trying to figure out. I think I'm supposed to either view this as going up the page like an information flow diagram sort of, that's either going up the page or down the page, but I'm trying to figure out which one of those it is. So it goes from eta to x, and then from eta, like the arrow, the little left pointing triangle and the right pointing triangle. So clearly, I think it's probably supposed to be going down the page, because as you can see here, eta, it has this like long arrow, which is not the same as the short arrow we usually see in normal lean for functions. But the point is that it takes in a unit, which basically means it takes in nothing, right? It takes in like the unit type, like a type with one element, no information actually present in the thing that it inputs, and it outputs x tensor y. So basically it's taking in nothing and it's outputting two outputs. And so I think that the way that I interpret that is that information is going down the page here. We have eta, which is putting out these two outputs, x and y. The y output is sort of getting absorbed into this epsilon here. The epsilon, in contrast to eta, is taking in two inputs and it's like outputting a unit, which is basically, it's taking in two things and then it's absorbing those two things. And I think the interpretation that we're supposed to have probably is that I think the interpretation we're supposed to have is that like when eta outputs something, just checking my Greek here. When eta outputs something that epsilon then absorbs, the point is that the other output of eta is supposed to be like equivalent to the other thing that the epsilon absorbed, because that would be like the thing that makes the string diagram work out, where you can wrap your strings this way and that. So that seems fine. Yang-Baxter. And then Yang-Baxter is, I wonder if I can get like a picture of the Yang-Baxter thing somewhere in this guy's blog post. String diagrams. Okay, if I like Yang. Wow, does oh yeah, this is something that's totally burned me before. When you do Command F on Firefox, the little box shows up at the bottom of the page, and I can't see it because the top of my laptop hides it from me, and I got like totally burned by that. So if I search for Yang, clearly Yang-Baxter does not exist in this file. Okay, that's fine. What if I just like scroll through? Yeah. Properties and rewrites. Yeah, so he sort of immediately gets into the cryptography, and I'm not sure that we're going to like get a good description of the fact. Maybe it's like this. I think this is a little different though. This is like this is this sort of barrier. I think it's not really clear by the by just the diagram alone, but from the context of what he's written sort of around this, I think it's meant to, this is not meant to be, this vertical bar is not really meant to be the same type of thing as the horizontal bars here. Yeah, so that, I don't know if I'm going to like find a good description of the Yang-Baxter lemma or whatever it is in this blog post. That's fine. Nevertheless, it's something that we have. Okay, example use of string diagram widgets. Nevertheless, it's something that we can simp only whisker left. This example, whisker right tensor. So what exactly are these examples? So what happens if because they don't make reference to these lemmas here. So what happens if I shift click on this? It says default. It doesn't give me any actual. G, however, does give me something. Okay, I'm starting to reinterpret this. So G, like when I shift click on G, it actually gives me an output, despite G not having actually any like structure here. G, the only thing about G is that it has this type. So it seems like the string diagram is somehow copying the type. It's like being a string diagram form for the type of G. And it's telling me that X tensor Y goes to Y tensor X tensor Y. X tensor Y, and F arrow X tensor Y equals G. Okay, so the point is that arrow, I think what's sort of happening here is that we have this rightward pointing triangle, whisker right operator of monoidal categories. Presumably that's this triangle here. Notation for the whisker right operator. We also have the tensor. So presumably the X tensor Y thing is for this part, right? X tensor Y goes to X tensor Y, and then we also have the X on the left-hand side goes to the Y on the left-hand side. And presumably that comes from F. And so the F whiskers this, and that basically gives you G, which has this other type. Monoidal category. So after I simp, okay, so what is monoidal category whisker right tensor? This is a lemma. I don't think it's a lemma that comes from this pull request at all. And presumably, unfortunately, I'm not going to be able to like see it written out. I'm not going to be able to see the string diagrams because this file does not import this, like the string diagram file, and presumably I can't make it import it because it probably like depends on it. I'd probably get like a circular dependency or something. Okay, I'm not gonna necessarily try to do that, but the point is that it's a lemma. The lemma has the following type: F whisker right Y tensor Z equals alpha xyz dot inverse notation for the composition of morphisms within a category. Okay, so we have alpha associator, the monoidal associator. Okay, yeah, yes, okay, this makes sense. It makes sense to me. This is like the associative monoidal associator. So it's a monoidal category, right? Which means that, you know, you can, if you have two arrows, you can actually sort of tensor those arrows together and get a new arrow which acts on the tensor of the objects and outputs the tensor of the objects. And the point is that it's a monoidal category, which means that in addition to having this, it's not like a magma category, right? It's a monoidal category, which means that in addition to being able to tensor the arrows, you can also presumably have association on the tensors of the arrows. And what this is presumably saying is that, like, if I have x and y and they're arrows and I tensor them, x is in C, either it's an object or an arrow. I'm not totally clear about that. C is a category. Can I look at exactly? C is a category, but is it this type of objects in the category? Ooh, okay, well, MCC is the category, sorry. Presumably this means it's the type of objects in the category. So category, the type class category C describes morphisms associated to objects of type C. Okay, so C is the type of objects for the category. Shit, I've lost my place. Let's go back to this definition. Okay, so here we have objects of this type. So Y and Z are objects in the category, and we can tensor those objects. Ah, yes. Okay. Maybe I went too far in my initial statement. In a monoidal category, you can definitely tensor objects in a monoidal category. You can definitely tensor objects in a monoidal category. Presumably you can tensor arrows in a monoidal category as well. I'm less certain about that. But what this lemma is referencing is, okay, so we're doing this, whatever this whisker right operator is for monoidal categories. Fortunately, it doesn't really describe what it is. Notation for the whisker right operator. It's notation for the whisker right operator. Okay, so can we get to the definition of it, or go to definition? Whisker right. Okay, it goes to the definition of the notation, but what I want is the definition of whisker right. Okay, monoidal category struct, an auxiliary structure to carry only the data fields of a monoidal category. Whisker right. So we have a monoidal category on C, on objects of type C. And what whisker right does is it takes two objects and a morphism from the first object to the second, and then a third object, and then, yeah, so this is a tensor, and of course the notation hasn't been defined here, but the point is that tensor x1, y, right, so this is with, yes, wonderful, yes, this is exactly what I was sort of expecting would happen. So what is whisker right? This is the thing that, okay, if I have x1 tensor y, that is an object. So I have x1, x2, and y. All of these are objects in the category. And because it's a monoidal category, I can also do tensors of objects to get further objects. So I can get the further object, x1 tensor y, and I can get the further object, x2 tensor y. Those are other objects that I can create using the tensor. And then the point is, like, okay, what do we know about the arrows on these new objects? And what this is telling us is that if I have an arrow from x1 to x2, I can get an arrow on the x1 tensor y to x2 tensor y, basically just by in the natural way, right? Like if I have a function from x1 to x2, then I also have a function from x1 cross y to x2 cross y just by operating on the first coordinate. And that's presumably what the whisker right is. Category theory is this pointless field of mathematics where you just generalize, very basic concepts. And so this is the very basic concept that is being generalized here. Okay. Wonderful. Tensor HOM. And okay, so like let's keep looking through. So presumably whisker left is the one that operates on the left-hand side, right? So if we tensor x and y1 and x and y2, then I can get an arrow between those if I have an arrow between y1 and y2. So I can whisker on the left, I can whisker on the right. Well, that makes sense. I can do tensor hom. What is this? Tensor product of identity maps is the identity. Tensor product of identity maps is the identity. Yes, okay, I'm fine with that. By default, it is defined in terms of whiskering. So if I whisker right fx1, fx2, yes, whisker right. Yes, so the explicit arguments to whisker right are only the function, sorry, not the function, the arrow, the morphism, right, and the other object, right. So those are the only like explicit arguments. The other arguments are implicit. And so what tensor hom is saying is that if I tensor x1 and x2, and if I tensor y1 and y2, just defined in terms of whiskerings. Whisker right f. Okay, so it is, what is tensor hom? Ah, yes. So this is basically just defining two whisker. It's basically doing two whiskers at once, I think is what's happening here, right? It's like if I have x1 and y1, and if I have x1 and y1 and x2 and y2, and I have an arrow from x1 to y1 and an arrow from x2 to y2, then I can tensor the x's and tensor the y's and tensor the morphisms as well. And what I get out of the tensor of the morphisms is just, if I were to like compose the whiskers. That's if I were to do them one at a time. Now, do I have to be able to... So this, like, I wonder if there's like some theorem or something which says that like if I... So this is the composition of morphisms, right? And what I sort of wonder now is if I were to do the whisker left first and then compose it with the whisker right, would that also be the same thing? Like, is that a theorem? Is that because that would usually be true, right? If I were just thinking about functions on sets. So I don't know if that's like a theorem or if it's something that's only like there's another name, this is a monoidal category, but that would be a monoidal category with moving of tensors or something. There's lots of different names for things in category theory. Tensor hom. Let me just look. I don't necessarily see it. Defined in terms of whiskerings. Yeah, interesting. I'm not exactly sure, but maybe it's like some theorem that will pop up later. So the tensor unity in the monoidal structure. Yes, tensor unit. Okay, well this is just very sensible. So we have the tensor unit, right? This is just the object, right? There's like a one object. So the objects themselves form a monoid that you can tensor the objects together. But there's also like a base object, which if you tensor onto it, you just get the like basically the same object back, or something equivalent to the same object back. And so that's what the tensor unit is, presumably. And then we have the associator, which says that I can tensor objects in whatever order, and it's the equivalent notation for an isomorphism in a category. Yeah, presumably that just means there's an arrow either way. Yeah, this is like my lack of knowledge of category theory is showing isomorphism in a category. Isomorphism is an invertible morphism. Presumably it's just a morphism one way, a morphism the other way, and the fact that they're both equal to one. Yeah. Yeah, so that's what an isomorphism is. Great. So yeah, so there's an isomorphism. The point is there's an isomorphism between the tensor objects in one way and tensor objects in the other way. Okay. Left unitor. The left unitor. For all objects in the category, if I tensor the unit onto X, then I get something which is isomorphic to x. Yes, that's totally acceptable to me. And the same thing is true on the right. Okay, cool. Wonderful. So now I've learned a lot about monoidal categories and everything that comprises them. So let's return. Sorry, I didn't want this. I want to go back. Let's close this and like return to the whisker right tensor lemma. So this is a theorem, whisker right tensor. And so let's like recall what the whisker right operator is that we just looked at. So whisker right is you take a function and you take an object, right? And the function acts on like two other things. And basically the point is that if you apply the function onto one, it's equivalent to, if you had whether you apply the function on those objects before or if you apply them after, tensoring those objects with another object in the category, that's basically fine. And so what is it saying? What is this theorem saying? Whisker right tensor. It's saying that, okay, like let's intros. Let's like follow along the lean proof here. So in this case, we're assuming that the like additional object that we're whiskering onto is itself a tensor product. And we're saying that if we whisker a function onto some tensor product, then that is, okay, what is the mono? Oh, this is the associator. Okay, so this is the associator that we saw, which basically just means that, it's an isomorphism between xyz and xyz. So, right, basically, I think a lot of the point of category theory is that you're just supposed to ignore a lot of these things, right? So the associator, just like forget about the associator. Just sort of think of these two, like different composition orders as identical, right? So like I'm taking the associator here. Technically, I'm taking the inverse of the associator. And I'm composing that with f whisker y whisker z. Sorry, let me just make sure that I'm getting the so f whisker y, and then, so if I f whisker y, yes, this makes perfect sense, right? If I whisker f onto y, right? And then, so that gives me now a function between x1 tensor y to x2 tensor y. Just want to make sure. Actually, it looks like they're x and x prime in this case. So f whiskered on to y here is going to be a function from x tensor y to x prime tensor y. And then I can whisker that onto z, which will now give me a function from, I should really say arrow, an arrow from x tensor y tensor z to x prime tensor y tensor z. And then I can simply apply the associator back and get something from x. So basically the associators on either side, what are they doing? They're basically just making sure that the parentheses are here between the y and the z, rather than between the f and the y, right? And then with the z on the other side. So this is the whisker right tensor. Okay, so what have I learned? I'm not entirely sure, but this is the whisker right tensor, and that is what's happened. So let's pop back up the stack. We have f whiskered on to x tensor y. The point is that if I simp only this, then I get a bunch of whiskers rather than, and then some pointless association jumblings. Who cares about how things associate? Basically, the point of this is that f whiskered onto x tensor y is equivalent to f whiskered onto x whiskered onto y. So that's the lemma we are applying here. And then we say sorry, basically, because this is exact w.lim, and that's sorry. The widget doesn't work. Now the widget works. Interesting. So the point is the widget doesn't work here. Like if I click here, shoot, I was not supposed to click that. What I was supposed to click was shift click is to click. It doesn't work here. But it does work for G, doesn't it? Yeah, that's interesting. It says the widget doesn't work, but it does work for G. The point is that G, yeah, so this is the thing. It's like this sort of function, right? You think of G as being a function that takes in x and y and returns a y and an x and a y. But after I apply the whisker right tensor, it's saying to me that now everything is copacetic. So if I shift click, yes, very nice. So the thing is, I'm a little bit nervous that x. This is a little weird to me, because I'm sensing that instead of x here, it should be something like the identity map. This is the identity. Presumably, this is like the identity map on x, right? Or maybe it's maybe that's not what it's supposed to be. Right, so like in actuality, we know nothing about what these morphisms are. So this is not like a theorem that is true in general. It only works because we have this sort of like sorry in it. So the point, I guess the point is that like I can observe this and I can observe this. And I can observe that, you know, you can either think of them, this is like, I'm sure there's something in the like the diagrams here that is sort of analogous to this. Let me see. The point is I have A and B. Yeah, you see here is like composition. The order doesn't matter, right? We have A tensor B, and it's, you know, it's the same as applying one or the other. I don't know if I'm like getting a very good image to sort of represent what's going on here. One is like we can think of A and C as like one operation, right? That's sort of like having G in the middle here. Or we could think of them as sort of separate operations that are all happening in parallel, and that's the like top here. So like my very rough claim is that like this side of this diagram sort of corresponds to the top here, and this side of this diagram corresponds to the bottom here a little bit. And then we have the same example, but for whisker left. Yes, F is whiskered onto the identity map on C. What is this? Sorry. This is the tensor unit, right? Yeah, so F is tensored onto the unit. The widget doesn't work, then the widget works. Okay. So let's see, like my goal, my sort of rather ambitious goal was to try and replicate this proof from the paper in diagram 6. This proof here. So this is like the security proof of the one-time pad. And basically, right. Basically the point is that, you know, you can think of the one-time pad. So like what is happening? Maybe I should just like talk through what is happening in this like pictorial proof of the security of the one-time pad, just to like, you know, ground myself. So the point is that you can think of the one-time pad as like an information. This is like an information flow diagram for the one-time pad, and you have Alice here, right? So Alice is here and is trying to communicate with Bob. But Eve is the eavesdropper, and Alice is going to send a message, and then that, I guess the point is that that message is going to get, okay, so actually probably it's better to like look at the ingredients, right? Right, so this is like, here you can see what all the like individual parts of the protocol are doing. So there's this copy, right? So like the information goes up the page, and this little part of the diagram basically means you've taken something and copied it, right? So you have some input here, and it hits this little dot, and then it's copied, and then now you have two copies going off in two directions that you can feed to other things. And I guess you can label all of the like things, all of the inputs and outputs with like who is providing the input, who is getting the output. So this is Alice's copy map. Alice can copy something on her own computer, and Alice can broadcast to Bob and Eve by copying something and then sending one copy to Eve and one copy to Bob. And we also have this random shared key. So the little upside down triangle here presumably means like generating randomness. And the point is that like in a one-time pad, it's assumed that Alice and Bob have a shared random key, right? So the point is that someone like, who knows who has generated some randomness, some like trusted party. Maybe it's Alice, maybe it's Bob, maybe it's like Alice in the past, who knows? They've generated this random key and given one copy of the key to Alice and one copy of the key to the Bob. So the triangle is the generation of the key, and then the little splitting here is the copying of the key, and one side goes to Alice and one side goes to Bob. Okay, so all of that is very good. Then we have in figure 5 a whole bunch of local ingredients, right? So this is a whole bunch of like axioms, right? So what is happening here? I think the point is that, so this is like a little upside down version of the copy diagram, but I think the upside downness is meant to communicate that we're like adding things. We're doing XORs of things. Is there some reference to that somewhere? Where it confirms that is like you're doing the XORing. Surely there must be some point. Because that's what this happens, right? Like you're supposed to XOR the thing with the key, right? And so clearly that's what Bob is doing. But where does it actually say? Maybe in the description. Just figure 5. Multiplication, right? The local ingredients of OTP and the axioms they obey are depicted in figure 5. Correspond to a Hopf algebra, who knows what that is, with an integral in a symmetric monoidal category. Any finite group gives rise to such a structure. The integral given by the uniform distribution. Yes, okay, so it's a uniform distribution. Concretely, this means that Alice Bob must agree on a group structure and on the message space. The fact this multiplication forms a group and that the key is random can be captured by the equations of figure 5. Okay, so I mean it doesn't make it as clear as I would like, but yeah, so you can sort of see how it's supposed to be a group, right? So the point is, if I have A, B, and C, and if I add together B and C, and then with the result, I add A to the result of that, that is the same as having A, B, and C, and adding A and B, and then adding the result to C, right? So those two things are the same. In fact, it's more like a monoid than a group. I don't because the point is that this part of the diagram here represents the associative law on the XOR operation, right? So we can do the XOR of bits, and it doesn't matter in which order we XOR them. It's the same either way. And so we can, if we have this diagram, this as part of the diagram, we can rewrite this part of the diagram to look like this, and everything will still be equivalent in terms of what's sort of happening in terms of information. And then, so we have further things. What do we have as further things? So here we have yet another new diagram component, which is this gray dot with nothing below it. And I think what the gray dot with nothing below it, I think is meant to represent the identity of the group, right? Because what this part of the diagram is representing is the fact that if I have some value and I take the identity and I multiply the identity, if I take the group composition of the identity with something, that is literally just the same as taking that thing and just passing it forward without doing anything to it, right? Because you multiply the identity, it's not supposed to do anything. Or you add the identity. I guess we should think of these as additive groups. So I'll say add. If you add 0 to something, that does nothing to it. And so this is the little 0 of the group, And similarly, you can add it on the other side, and that's also the same. You're literally just passing it forward, and so that's represented by this like vertical line here. The vertical line is literally just you passing it forward. So that is what this set of equations is. And so like these two equations sort of between themselves represent like the group or monoid properties of the like multiplication. Now we have this, which is sort of an upside down version of the associative law. But remember that when it's upside down like this, so this is it's sort of upside down, right? This is addition in the group, but the upside down version is copying. And so what we have here, I guess, is if we take something and we copy it, and then we copy, we have two copies right now, the left copy and the right copy, and then we copy the right copy into two more copies. We basically just have three copies. The whole point of this equality here is, if you copy something and then you take one of the copies and copy it again, it's all the same as just making three copies of literally three same copies of the same thing. And so it doesn't matter like which order you copy things in. And so that's basically what this is. It feels a little weird that it's sort of like at the same time interesting and weird, because it's definitely the exact upside down of this, but it sort of represents something different, right? It represents the copying operation. I don't really understand if there's something like really deep going on with the fact that you can turn things upside down. It seems like it's sort of this weird coincidence that the upside down of copying is multiplication. But like this is just representing the fact that you can copy something three times. Okay, now we have the upside down of this sort of identity operator. And what is this saying? Okay, so now we've introduced now like a fourth little symbol with a gray dot. And this is just a gray dot that, so basically a line just goes into it and it disappears. So the way I interpret this gray dot now is that it's just like deletion. Basically, you could think of this gray dot with one line going up into it and then nothing coming out of it. You can just think of that as deletion. And the point is that if I take something and I create a copy of it and I delete one copy, that's the same as just passing the thing forward. And so that then is what this sequence of equalities is. Okay, so now we have this this statement here. Something interesting is going on here. So what's the right hand side? The right hand side is we take two things, we multiply them, and make two copies of what we've multiplied, and then pass those through. And what that is saying is if you take the things that you started with, right? Okay, so on the left hand side, we have our two inputs, and we're immediately copying them. On the right hand side, we have our two inputs, and we're just copying, and we're just immediately multiplying them. But the point is, I guess the point here is that it doesn't matter if you copy them first and then multiply the copies by themselves, or if you just multiply them immediately. Either way, it's the same. And that basically makes sense, right? If I need two copies of the multiplied thing, I can either make two copies of the individual things and multiply them, or I can multiply them and make a copy. That sort of makes sense. And so that's the information flow here. Okay, here we have yet another symbol, which is this little I. And presumably the I stands for inverse. So here we have some value going in. That value gets copied. One copy, we take the inverse of that, and then we multiply that, and it comes out. So the point is that should be a 0. And indeed, that's what that is. Right. Okay. So this is great. So right, remember, like, the last time we saw this little dot with nothing coming into it and one thing coming out to it was up here, and we decided here that it basically means the identity of the group, right? The 0 of the group, where if you multiply something by the identity, you just get like a straight pass-through, and nothing happens. And so what we're seeing here is that we take something, and we take something and the inverse of that thing, and we multiply them together. That's just 0. And the point of this part down here is that, whatever we started with, we've effectively deleted it. Like if we start with something and then multiply its inverse onto itself and then do nothing else with that thing, then we've effectively deleted that thing. So that is why this part of the diagram is equivalent to just like taking some input, deleting it, and then returning a 0. So that's totally fine. And then there's this. So again, this little upside down triangle is supposed to be sort of like randomness, right? It's like a uniform randomness, which is probably why it's called like the integral, the uniform distribution, right? And the point is that if I take something and then multiply it with randomness, the point is that the output is random, and that's basically also, you've deleted the thing you've started with, right? So just like here, you basically are deleting the thing you start with if you don't like use it in any other way. Basically, if I multiply something by randomness, that like destroys all the information. So what we're left with is just randomness coming out. Okay, so that covers all of the local ingredients of the one-time pad and the actions they obey. Wonderful. And so now we are ready to think through the actual one-time pad, right? So this is a one-time pad, right? If we start here on the very left-hand side with the one-time pad as it is usually described, right? We have some randomness, which is given to Alice, right? So what to think of the different parts of this diagram? I would say that the line between these two dots here, that sort of represents the clear text, that sort of represents the message that Alice is the encrypted message that Alice is sending, right? So Alice gets a message. In a one-time pad, she encrypts the message by XORing it with the one-time pad, which is what is coming out of this randomness box here, right? So Alice XORs with the one-time pad, and then she sends that message. And the point is that there's the eavesdropper Eve who gets access to that message then, and also Bob who gets access to that message. But Bob additionally gets access to the inverse of the one-time pad. And the point is that Bob is supposed to take the message and multiply by the inverse of the one-time pad to get out the true output, whereas Eve is not supposed to have anything. And I guess the point is that we can do a series of transformations to show that this, like what we start with, is equivalent to Eve just receiving randomness and Alice just passing something directly to Bob, which is what we want, right? We want Alice to be able to send a message to Bob. We want Eve to have nothing. So what is the sequence of transformations that we do? The first sequence is this sort of, so the first sequence is this sort of multiply. It's like you could call it the commutativity of copying and multiplication, right? Here we multiply things and then we copy them. That's the same, right? It's this right here, right? It's the same. Multiplying two things and then copying them is the same as making copies of both of the things and then multiplying them individually. So that is what has been done in equality 1 here. Then we do equality 2. Equality 2, I think what has happened, so basically this part, these two things, previously that Bob's output is coming from the right of these two dots here, and then on the other side it's coming from the left of Bob's two dots. So what I think is happening here is this it's this part of the equation, right? It's basically the group associativity law, right? If I take this output and then I multiply with whatever Bob's one-time pad is, that's the same as, multiplying them first and then going in the other direction. And like addition, so we've applied that, and we've also sort of done like an application. So that is how this transfers to this, and then there's also how this part transfers to this part, which I think is an application of this like copying commutativity law, or copying associativity law. Not sure. Commutativity, associativity. Who knows which ones are which? But so basically, an application of this equality and an application of this equality have both happened here, and that gets us to through equation 2. Then equation 3 is basically the removal of this structure, right? We saw this here. Like whenever we have this structure where we take something and we copy it and multiply by the inverse, that's the same as like just deleting the thing we started with and passing through the other thing. and passing through like a 0. And so basically it means we can delete this little substructure here. And so that substructure like comes apart and they get disconnected. Now we start applying the sort of like simplification. You can sort of think of the rest of the things as sort of simplification steps, right? There's for example, there's this simplification where if I multiply 0 by something, that's just the same as passing it through. So basically this whole structure, like these two lines in this structure can be deleted, and it just passes through, right? So now we just have a line from Alice that goes directly to Bob, basically. And the same thing can happen here. Like this is a randomness, and it's coming in here. And remember, so I guess we're doing a couple simplifications here, right? If we copy something and then delete one of the copies, that's the same as not doing anything, right? That's what's exemplified here. And we're also using the fact, which is here, which is, okay, I guess that's what we do in the next step, right? So after we delete those two substructures, the little randomness thing, I guess the randomness has been like pulled up near the E, so that's a little bit easier to see. But now that we have this substructure, we can do equality 5 and replace this substructure with the separate randomness and thing, right? Which is an application of like this law here. And then we can do a final application of the little collapsing, and we get the final output, which is what we wanted. Okay, so that is the like string diagrammatic proof of the one-time pad. So what would I need to actually be able to like see what my goal is, I think, is to like be able to see each of these steps. My goal is to basically be able to see each of those steps. And the point is that it's sort of And so I think like, what is my plan here? It seems like what will probably have to happen is that all of these axioms that appear in figure 5, I'm about to like, I noticed that like I was like, in order to get this to work, the author of this PR had to call this simp. I'm just gonna like quickly see if like simp gives this. Yes, okay, so like simplification works for monoidal categories as well. And so they had to like simplify things in order to like get the whatever like the simp theoretic normal form for category theory is. So now I want to be able to do the same thing. Right. Right. So what actually, so I'm basically what I'm thinking is that each of these little equalities here is going to probably have to appear as a hypothesis to a lemma that I write. So why don't I just like start writing a lemma? Yes, clearly they did not end their section. But what I want to do, okay, so let me start to write a lemma. Lemma. The name of the lemma will be OTP. Yes, it's not, the AI autocomplete is not being helpful. I think what is about to like happen is that what I'm going to want, yes, so I'm going to want like in the Yang-Baxter lemma here, let me like collapse the info view for a second. In the Yang-Baxter lemma, they have this theorem, this hypothesis, which sort of constitutes a theorem about all V1 and V2 in the category. V1, V2 is V2, V1. The Yang-Baxter. I mean, is the point, It's interesting to me, like, why is there, sorry, is this just that you know, the category theory library is incomplete and there's not actually like a proof of this Yang-Baxter, like can I contribute to the category theory library by like proving this Yang-Baxter lemma? Now, not obvious. I don't think I need to do that. What I think I want to do is start writing a bunch of like for all statements that sort of like capture. So, oh God. Okay, so yeah, sure, let's have a few of those. And okay, so what did I say this was? I said that this was like the associativity of the XOR, right? So I'm gonna say like XOR a sock. And it's suggesting something, but that's not what I want. What I want is for all, and the Yang-Baxter calls it v1, v2. So I think for all v1, v underscore 1, v underscore 2, v underscore 3. Definitely this. Is this what I want? Tensor. See, I think the problem is, I think that this operation, right, the XOR operation is not like just tensoring. Like if I AI autocomplete this, that's fine. Unexpected and yes. False. Sorry. Okay, so it's happy. It's like it's basically happy with that, but that's not. I don't think this is what I want, because I'm saying this is not right. This is what the associative, like this is if I return to this is if I return to it's in one of these lemmas here. The alpha, right? This is the monoidal associator, right? That's not exactly what I want. The monoidal associator. Yeah. Oh, that's interesting. The monoidal associator. That's sort of interesting in that, like here it's a 2 equals tilde, and here it's a 1 equals tilde. I wonder what the meaning of that is, or if it's intentional at all. Associator, the monoidal associator. So I think that like the point is that I don't want this. What I want, what do I want? I want an operation. What I think I want is to like actually define. Here's what I think I want. I think I want XOR. What I think I want is I want like an XOR operation. I'm about to do something wrong. I'm about to like have a brain blast. What I think yes. Oh. For all v1 and v2 and c. I think, here's what I think I want. For all v1, v2, and v3, what XOR, for all v1, v2, v3, the XOR operation is an arrow from v1, v2 to v3. Yes, like, it's sort of confusing because I don't really understand what the objects of the category actually are. But I think that they should be thought of sort of as like the registers, right? Like register points in time, right? They represent like values of a register at a point in the protocol. And the point is that there can be an arrow which sort of indicates. So that, like, what I'm trying to get at with the XOR here is this sort of this little operation where like two things come in and something comes out. And it's basically the point that I want to be able to apply it to anything. So I have XOR. Let's see, like if I can use XOR to define this other thing. So what I want to do is to get a hypothesis for this first thing. So XOR, yes. So it'll be a bunch of arrows. I think, yes. So actually there are 4 arrows. Like, so if you count it up, right? If you count it up, there's 1, 2, 3 inputs and a 4th output. And similarly, there's 3 inputs and an output. So I think I actually probably want like 4. If I'm saying the objects are like register value at time, then this is more like what I want. I want 4 things. And okay, so the point is that I can, the point is that if I do XOR v1, sorry, if I do X, so let me just try and start writing this out. If I do, okay, so I do XOR of v1 and something. So I'm thinking of them like this, right? This is v1, this is v2, this is v3, and the output is v4. So I think if I XOR v1, XOR takes in v1, v2, and v3. v1. This is going to get a little weird. Do I have to like name additional arrow? Because like, what about the output here and the input here? Like the XOR is an evidence of the relation between these things. I don't know if I really like or understand that. The point that I was like trying to do was XOR v1, v2. What happens if I AI on complete? Yeah, it doesn't even type check. What I want to do is XOR v1 with the XOR of v2 or v3, right? Like, so what is the like wrong thing that's happening in my head that is not what I want? XOR v2, v3. Right. The point, the point is that I'm wanting to XOR the output of this. The problem is that XOR does not take 2 values, it takes 3 values. What is Yang? What is like the type? Let me like consider more carefully what is actually like the type of Yang Baxter here. Let me boot up the view. This is a really long ass type. V1, V2. Whisker. Yes. The point is that I'm wanting to like whisker things, presumably. Yes, I have to think about things probably more in terms of the whiskers. What is happening in terms of the whisker? What are the arguments to the whisker again? Whisker right. Let me just go. Whisker left, whisker right. You can go to the definition. And then through the notation definition to the definition. Point is that if I have whisker right takes in 2, it ultimately takes in 3 objects and an arrow from object 1 to object 2. And it's sort of an arrow from the like tensor objects. I have to think more about like what are the objects that I'm dealing with, like, because really they're like tensor objects, right? So what I have at the bottom is tensor v1, tensor v2, tensor v3. If I think those are the arrows, like, so if I'm saying those are the 3 inputs, really this is an error. Really this whole, right, if I think of this information thing as a whole, right, it's going from the bottom where there's 3 objects and to the top where there's 1 object, but you should really think of it as not 3 separate objects, but like just something that takes 1 big tensor object to the top, which is just 1 object. So presumably the point that I'm trying to establish is that if I have, right, basically the point is that on the left-hand side, I have an arrow from tensor v1, tensor v2, tensor v3 to v4. Is that right? Let me like do this drawing click. Or v1, v2. Yeah, because I sort of sense that like R v1, v2 is supposed to be this thing that like, you know, it's just like the permutation. Right, so R, right, R is something that takes in v1 and v2 and it returns v2 and v1. This is a little, yes, but what is the like middle here? That's the thing. If I add like a v5. v5, v6, we're adding a lot of objects here. I think the point, I could like try that to just sort of, am I wrong that it's yeah, the tricky thing is that I don't necessarily want it to like R here is doing like a swap of the v2 and the v3, and that's fine because it has v2 here and then the v2 goes here and then the v2 goes back over here. But that's not what I want. Yeah, not a lot of overlapping. Is it like a problem that I don't think it's like a you know, planarity is not that important, right? So that's not actually what's going on here. Is it that it's supposed to, the XOR, let me try just like think about what I'm like saying that I want to describe. What I want to describe is that if I XOR v2 and v3, like I'm about to add more things. The point is that if I have an XOR from v2, v3 to v4, what happens if I just like add more v's? Let's add more v. Let's like just go ham on the v's, and we can sort it out later. v6. Okay, we're getting in a territory where we have to make a new line here. So we have an XOR from okay, so let's say we have v1, v2, v3, v4, and let's call this line here v5 and this line here v6. So what we are saying is we have an XOR from v1 and v5, right? v5 being the output of the so we're talking about the left-hand side of this equality. v1 is the left-hand input to this, and v5 is the right-hand input. So what I'm saying is I have an XOR from v1, v5 to v6. I am also saying that I have an XOR from v2 and v3 to v5. v2, v2, v3, v5. And what is the operation? And this is where I sense that like whiskers are about to enter my life. Basically, the point is that all of this together becomes some arrow, right? It's like the XOR is an arrow. So this is an arrow, right? What is it an arrow from? It is an arrow from v1, v2 to v3. What? Like, what? Okay. Okay. Let me just like make sure. XOR. It takes in 3 objects and returns an arrow from the tensor of the first and second object to the third object. So what I want is an arrow. So I start with an arrow, like the whole thing is an arrow from one tensor v2, tensor v3 to v4. That is what the whole thing should be. Sorry, did I say v4? I think I'm saying the output is v4 and the intermediate wires are 5 and 6. So let's do that. So I have a XOR. The thing is, XOR also takes, the thing is XOR outputs an arrow. Yes, it outputs an arrow. So, outputs an arrow. The thing is, it's sort of hard to think of all of the types at play here. So I can sense that there's like something I have to do to, sorry, how do I write this? GG. Right, the composition of morphisms. So yes, so what I'm trying to do is I'm trying to compose morphisms here. What I think I want is what I want to do is establish an equivalence. How do I write the like equivalence of, how do I write the equivalence thing? Whisker right tensor, go to the definition. So it's an equality, maybe it's, okay, I'll just write it as an equality for now, and if it yells at me that it's not like technically an equality, I'll say it something else later. The point is, I want to take v2, v3, v5, and the XOR of v1, v5, v1, and v5 into v4. And the point is that that should be the same as, like, I have the XOR from v1 and v2 into v6, and the XOR of v6 v3 into v4. Of course, it's not telling me. Yes, application type mismatch. Argument XOR v1, v5, v4 has type v1, v5 into v4, but is expected to have type v5 something. It is expected to have type, yes. So let's start thinking about the types. What type should it have? Well, it should have the type. What is the type of this as a whole? What type do I want for this as a whole? What the type that I want, what I want the type of this thing, the left-hand side of the equation as a whole, I want that to have the type of an arrow. What do I want? I want it to be v1. How do I do the tensor product? Aux. V. I don't know if I'm. And how do I do the arrow? Hom. V4. Sorry, I'm just gonna like. Okay, so XOR, yes. Okay, XOR. And so I'm a little bit optimistic that like this side of the thing is not completed now, but what is this side complete? Argument v2, v3, v5 has type v2, v3, arrow v5. Right. Let me think carefully about this. So this is a composition of categories, right? Like I need to like map out the category theory here. The point is that I'm trying to compose the first operation and the second operation to get a third operation with the category, right? So the final arrow I want is this. I want to get this by composing two arrows. The first arrow, right, like so going up the screen, right? The first arrow is like the one is, so basically I want it to be an arrow from v_1 tensor, sorry, aux, right? And then on the other side, I want v2, v3, right? Because v2, basically on this side, we have v2, v3 going to v5. And that, yes, so the first arrow I want is v1, v2, v3 goes to v1. Yes, I'm getting it. This is sick. v5. This is what I want the first arrow to be. The second arrow is v1, v5 to v4. Yes. So these are the two things I have composed. XOR this, XOR v1, v5, v4 is an arrow of exactly that type that I want, right? And so now all I have to do is make sure that this arrow here, just making sure. Maybe the first arrow, okay, so I said the final arrow, right? Of course, yes, the associativity, let's deal with the associativity later. Let's put this here to make it like this. And so I'm just gonna say for now I'm just gonna say this. The final arrow I want has those two grouped together. And so now what do I want this? Here's where I do a whisker, right? This is presumably the left whisker. Let me just check the whiskers. Check my whisker order. Where's the whisker? Go to definition of whisker. Whisker right. So basically I have an object. The point is that I have an object. Going by the string diagram. I have an object on the left, which is doing the same. And then I have an arrow on the right, which I get from the XOR. Oh, I'm so close. I'm so close to like the very first part of it, but I can feel I'm making progress. Okay, so I have the object on the left. I think I'm doing a whisker left. Right? I have an object on the left, an arrow on the right, and I'm whiskering them on. And so what I want is the whisker left. So what I think I want is, yeah, the v2, v3 goes to v5. This, I'm whiskering left onto v1. v1. Okay. The whole left side of this equation type checks. Sick. On the LHS. Okay, so like curiosity, what happens if I do this? It still seems to be fine with it. Interesting. It's still fine with it. Sorry, wait, what is the order? What is the order? What is the order of binding? How does this work? Is this I forget how it binds. Does it bind on the left or the right? Here, I need to use the restroom. I'll be back in a moment. Okay. I don't know. Let's take a look. Wonderful. We have some tensors up here. If I go here and I activate the info view and I mouse over, yes. Okay, so it binds the tensor obj function, which is this tensor product, binds on the left and not on binds on the right and not the left. I don't know. You know, if I like, there's no parentheses here, but if I were to put parentheses here, they would be around the right two things. So the point is that this is syntactically equivalent to this. And so it was not necessary for me to write that. So what am I saying this is equal to? Okay, so now the final arrow I want is this. On the left-hand side, I want to get this by composing two arrows. The first arrow was the v1, v2, v3 goes to v1 and v5. And then I want to go from v1 and v5 to v4. On the right-hand side, I want to get this by composing the two arrows. Okay, so for the right-hand side, now we're talking about this side of the equation. The first arrow, okay, so yes, recalling, v1, v2, v3, and I'm calling this v6. I don't know if it's supposed to be the same as v5. I don't think it's supposed to be the same as v5. So v1, v2, v3, v6, and v4. So the first arrow I want to do here is the arrow which goes from v1, v2, v3 to v6, v3. v1, v2, v3 to v6, v3. The second arrow will then go from v6, v3 to v4. So how to write this? So now I want to whisker on. Previously, this was a whisker left. Now I want to whisker right. LHD. And whisker right is RHD. Okay. So I want something, yes, so again, it's like a deal where I whisker. Sorry, what's that, like, in the whisker note? Sorry, what just happened? String diagram of widget. I don't know what that is. That's the, like, the LaTeX code or whatever. Whisker right, I have a function and an object. So the object goes in the direction. So what I think I want here, let me just start writing it in parentheses. I want, okay, so I want something, yes, lots of parentheses here. I want the XOR of v1 and v2 onto v6. v1, v1, v2, v6. I don't think the AI is telling me the right thing. I want that right-hand whiskered onto v3. And then I want the result v6, v3, v4. Yes. And it's complaining now, but it's complaining because the associativity, I've gotten the associativity wrong. Unexpected colon, expected. Is it not complaining at all? Wait. Sorry, let me like put this here. This is the associativity. Okay, so now it's going to be complaining about the associativity. Yes. Has type v1 tensor v2 tensor v3, but is to something, but is expected to have the type v1 tensor v2 tensor v3 to something. So it's got the associativity wrong here. So what I need to do now is correct the associativity. So how do I correct that? Let's look to the Yang-Baxter statement. So what it like? So this is the notation for the monoidal associator. .hom, the forward direction of an isomorphism. Yes. But the association is okay. So let me like write more clearly. On the right hand side, what I want to do is this. But this doesn't match due to associativity. The activity of the list. Therefore, I need to use the monoidal associator. Monoidal associator. So the monoidal associator, let's like mouse over that again. It is something that is an equivalence between x, y, z, x tensor y tensor z to x, y, z. So I think I want the inverse of this, right? So basically, I think the first, yeah. So before the first arrow, I shall do the associator gives me the arrow v1, v2. Okay, at the end of the day, the final arrow I want is the one that's associated correctly. So what I want is the one that will go from this to that. Wait, no, that's the natural one. The unnatural one is this. Right? The associator goes from the unnaturally associated one to the naturally associated one. So what I want is the inverse. The inverse then and then so I'm so fucking close. I can do this, and what I want to put here is the inverse. I think I can do this and not hom but inv. Oh, I type checks. I'm so good. Yes. Okay. Oh yeah. Okay. Yes, interesting. Okay, so the point is that there are like these weird v5 and v6 that like hang out in the middle. There are these, you know, these, all the lines, basically all of the lines, all the wires, strings, I guess you call them, in the string diagram are like, they correspond to particular objects in the category. Even the intermediate wires seem to have like an object associated with them. Associated. An object related to them. Okay, so that's XOR association. Should I just keep going through? Should I keep going through and doing all of these like equalities here? I guess. Maybe like at the very worst, I'll gain like a lot of experience with the random notation here, and the whiskering and the tensor producting and the like monoidal associator. Alpha underscore is the notation for the monoidal associator. Interesting. I wonder like how standard that is. It's monoidal associator. This is something that's associated with like a monoidal category. Of course, it's a symmetric monoidal category. I think that's like an additional thing. It's a symmetric monoidal category, and presumably that means that that's sort of what the R is here in Yang-Baxter, maybe. Like it's symmetric, and that there's like this canonical map from V1 tensor V2 to V2 tensor V1. probably called the monoidal commutator or something. I wonder if I can find like the definition of symmetric monoidal category. Let me like go on a tangent. Symmetric monoid. Maybe it's just SMC. Let me search the docs. MathLab docs. I don't want the MathLab 3 docs. MathLab 4 docs. Is it symmetric monoidal category? I wonder if like Moogle would give it to me. Moogle. What is Moogle? It's like supposed to be. Okay, well apparently it's a fictional character from Final Fantasy. But what is Moogle lean is what I'm looking for. Okay, Moogle lean for this Moogle search engine. It's already used Moogle. A list of awesome lean for projects. Moogle, semantics. Can I get on it through here? I have no idea. Moogle AI, here we go. Yeah. Symmetric monoidal category. Ah, so there's two different type classes, one for symmetric category and one for monoidal category. And the combination of these two things. So what happens if I click on the symmetric? Extends braided category. Braiding, naturality, hexagon. Oh my god. We've got hexagons. Symmetry. Yes. Beta underscore. The braid relation. Braiding. A braided category has the beta. Ah, yes. So the beta is like the alpha, but for braided category. A braided monoidal category is a monoidal category equipped with a braiding isomorphism. X tensor Y is equivalent to Y tensor X, which is natural. Satisfies the two hexagon identities, whatever those are. But yes, you can see how like the beta underscore is sort of doing something very similar to the alpha underscore over here, where the alpha underscore is sort of like the association one, and then the braiding one is the sort of commuting one. Interesting. All right, learning things about category theory. Anyway, that's a fun diversion. Is it important for my purposes? I mean, technically it is. It might be. Like, it's supposed to be that you're supposed to be able to, like, exchange things, but I'm not exactly sure what we're going to need that. We'll see, like, at some... We'll see if we need this. We'll see if we need this additional braiding category thing. We'll see that later, though. Okay, cool. So... we have our XOR associativity. Let's return here. I feel like we've captured this relation. Now we want to capture this relation. Yes. Thin stock, right? Like, so presumably what I should be doing is not like giving all these things as arguments to this lemma, but I should be defining like a structure fin stock, which like stochastic, presumably finite stochastic. I should presumably be building all these like axioms I'm putting in here into like a structure of some kind. At least that would be the right way of doing things, but I'm not doing that. For now, let me just like deal with a single lemma. Okay, so now what do I want to do? Now let me capture. Okay, so I think. So there's two equalities here, but I think what I want to do each of these equalities will be its own separate. So the first equality here was the associativity of XOR. And what did I say this one was? This was the identity. Yes, this is like the left ID mul, right? XOR ID mul. And so it looks like, in this case, there's only one input and only one output. And additionally, this additional thing. I'm going to need the 0 at the XOR, I think. Let me like start copying and pasting code. So here, so I'm going to do, this is not XOR associativity, this is like ID XOR. And the point is that if I have a V1 and a V2 and a V3 for the intermediate thing, then what am I to think here? Yes, okay, so I'm thinking like these two, the top of this line and the bottom of this line, they're all on one line, so should they be the same object? And I guess I'm thinking no, because how would that be possible? Because like here, that's V1 and V2, and on the other side, there are other objects. Like, so I think I want this to be V1, this to be V2, this to be V3, and I basically want to say that like there's two sides to this line. I'm a bit concerned that we have a line with a V1 at the bottom and a V2 at the top with nothing between them. I feel like maybe it's supposed to be that they're one thing. So let me try doing them as if they were one thing. So let's say it's just V1. It's at the top and the bottom. Yeah, this is a little tricky. Because how am I going to manage that? Okay, I don't think let me try and do it the V3 way. The final, okay, so the final arrow I want is an arrow from V1, I think, just to literally V2. We're going to, on the left-hand side, I want to get this by composing two arrows. Yes. The first arrow is V1 goes to, so V3 is the name of my thing. So it's going to be V3, V1. And the second arrow is going to be V3, V1 to V2. On the right-hand side, I don't want to compose anything, please. I don't want to compose anything on that side. I want to just have an arrow. Okay, so the point is that, like, how am I getting this V3? The V3 is coming out of nothing. In addition to XOR, I need more. I need, for this whole algebra here, so there's the XOR, right? Very good, but there's also the 0. And this, what is this? For any V1, this is something that goes from nothing, and it is an arrow that goes from nothing to V1. V1. And it goes from nothing. And how do I reverse something from nothing? Presumably it's the identity. This guy. Notation for tensor unit. This guy. You are 0. Okay. Yes. This is how 0. So it's, you know, I start with nothing and then I have something to put in my register, which is 0. Yes. I have a 0. Let's just create something to put in a register. So that's 0. And the point is that the point is maybe the point is that, like, in addition to 0, I need something. Maybe the point is that, like, I also need, in addition to 0, maybe, like, literally the straight line that goes from one value to another value needs a name, like carry forward, the act of, like, carrying forward. Like, so let me try this. Carry forward. For all v1 and v2, I can carry forward v1 into v2. So v1 carries forward into v2. It's like a name for this arrow. And the point is that it's like, this is simply what it means if I, like, am going straight through. And am I going to need to add, like, an additional axiom that if I, like, carry forward and then carry forward again, that's the same as carrying forward once? Potentially. Okay, that'll be interesting. We'll cross that bridge when we come to it. So we have this carry forward. So I think I'm going to add, like, a but this doesn't clause. So on the left-hand side, I want to get this by composing 2 arrows, right? But I do not have v1 to v3 XOR v1. The way that I want to do this, the thing that this, like, in this case, the problem is that I can't just magically, I need to tell it somehow that it's 0. The 0 is the thing that's producing the v3. But the v3 is coming from a 0 here. Wait, what did the AI just tell me? Something about the monoidal unitors. I saw the flash of the AI telling me what it was that I needed, and it was this, the left unitor. Yes, this is what I need. I need the left unitor. So unitor. The left unitor is the thing that makes, the left unitor makes a little 1 appear. So the left unitor gives me the arrow, v1 to unit tensor v1. Then I can compose, then I can whisker. Now I can whisker. I can whisker 0 to get and it's XORing there, right? Yeah, so the XOR. Okay, so now I have to write. Now I have to write it all out. Okay. Here's what I think I need. The first thing I need is the left unitor. What's the notation for the left unitor? Is there notation for it? The left unitor is lambda underscore. Lambda underscore. Okay. Lambda underscore. Who goes into 0. No, it shouldn't be 0 v1, should it? It should be 0 v3. So I have the left unitor, right? The first point, okay. The left unitor is going to give me v1 to 1c to v1. Then what I want to do now is there should be a whisker here somewhere. What I'm doing here is I am left whiskering 0 left, right whiskering? Whisker goes this way. It should be 0, v3 onto v1. And then I should compose that with XOR of v3, v1, v2. Have I gotten something wrong here? Type mismatched. Has type. Did I whisker correctly here? The right whisker right. What does whisker right do? Fuck. Whisker right. Whisker right is when I have a function on the left and an object on the right. That's what I have, right? The function on the left should be the 0 of x, the 0 of v3. 3. Yeah, it should be the 0 of v3. Do I not have this right here? Maybe I need additional parentheses. Location, okay. This is where we have to start doing some okay, this is why, okay, so what is the argument? We have a little argument here that we're not informing. So it's the left unitor. The left unitor takes in an object, returns so the object that we're creating the left unitor for is v3, right? v underscore 3. Okay. Has type. No, it's v1. So that should be the left unitor for v1 because we're going from v1 to unit tensor v1. Yes. Okay, so that's what we want. Type mismatch. Has type v. Okay, no. We want the opposite. We want the inverse. Inverse? Because the first thing that we want to do is go from v1 to 1c tensor v1. What the left unitor does is go from this. So we want the inverse. Yeah, so we definitely want the inverse. So we want to go the inverse. It's still complaining though. Here, let me like put my separate things on separate lines. Complains. Type mismatch. Is the problem that it's not is the problem that this doesn't match this? Do I have to like fill in the second side now? Okay, so how do I get it from the other side? What the other side is the pass through, the carry forward. Carry forward v1 v2. For real? Am I really that good? Is the carry forward? Yeah. This weird carry forward. I wonder if the carry forward thing is gonna like bite me in the ass at some point, but potentially just very good. Yeah, okay. Very cool. Woo! Okay. XOR ID, the other side of this equation. We're just gonna copy all of this. I think I sort of want to put it on the left-hand side. We're gonna call it XOR ID v1, v2, v3. The final arrow I want is this. On the left-hand side, I want to get this by composing two arrows. The first arrow goes from v1 now to v1 tensor v3 from is, okay, I will tell me this, but the v3 coming from 0 here, we use the right unitor. the right unitor will now give me like .inv. I can whisker the 0. And then, see, the most convenient thing about the AI is it saves me from having to like type out all these little underscore characters. The right hand, which I do by carry forward. Okay, so now what is happening? It's just going to be like a straight for straight. Okay, so it's row underscore is the right unitor. Lambda, yes, lambda and row for L and R. Great. Row. Yeah. Okay, so we do that, the inverse. Now let's whisker it onto the right. So what is the notation? It's RH, this is like LHD. This. This is now XOR V underscore 1, V underscore 3, V2. Carry forward. Okay, sick. Okay, making progress. We have done, okay, there are over here, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 equality signs, and we have done 3 out of 11. So let's keep going. Okay, what is the next one? This one, okay, now we have reached the copy. This is the copy operator. This is the copy operation. The copy operation, yes. So we need to define now a copy operation. The community, we're about to go for like the associativity of the copy operation. So we have our XOR operation. A copy operation goes from V1 from V1 to V2 tensor V3. Cool. Of course, it should be named copy. So now we have the copy operation. So now that was the XOR associativity. So now we want to do the copy associativity. I wonder if it'll guess. Ooh, it was so close. Copy. Sock. Okay, well, AI gave me a bunch of stuff. Let's see why it's wrong. Unfortunately, it's like it wanted to do copy ID. Let's see if it does copy ID correctly. So it was wanting to do one of these equalities. Let's see if it gets it right. The final arrow I want, yes. So here we have V1, V3, V2, V1, V2, V3. The final arrow I want is V1, V2. On the left-hand side, I want to get this by composing the arrows from V1 to V2 and V3, and the second arrow goes from V2, V3 to V2. Sorry, it's not just copying this from before. Yeah, right. Let me ID copy. Of course, it shouldn't be we need yet another thing. So wait. This should not be ID. This should be 0 because we named it 0. But in addition to 0, we also now need delete. We need our delete operator, which is the dual of 0. Delete. For all V1, yes. You understand perfectly, AI. And now, is going to not coming from a going to, a delete. So this should not be called ID copy. It should be called like delete copy, and then copy delete will be the other one. So this is delete copy. So I guess this is like the delete is on the left-hand side. So we're doing the left-hand, we're doing this equality, not this equality. We're doing this equality. Delete copy, delete. And I might need to not be doing, okay, so I need to think about this carefully. The first arrow is V1 goes to V2 and V3. No. If I'm doing the left-hand side, it should be V3. The other one should be V3, V2. The second arrow will go from V3 to V2 to V2. But the V3 is going to delete here, so I can use... yes, I want to use the left unitor. Okay, so it's now at the end that I use the unitor. The first thing I do is this. Then no, the point is that now it will be going from V3 to this. And now what? Tell me. Yeah, well, you just repeated my line above. So the third arrow. Yes, the left unitor. Carry forward. Again, it's like just a carry forward. Carry forward. Okay. And now AI will just give it to me straight. Okay. So the first thing I do is I copy V1 to V3 and V2. That looks great. The next thing I do, okay, it's not carry forward here. Equals carry forward. This should not be a carry. There shouldn't be any carry forward on the left-hand side of this equality. The next thing I do is the delete. It's a whiskered delete. I'm whiskering the delete operation. So whiskering the delete operation. So previously I was whiskering onto V1. Now I'm presumably whiskering onto V2. So it'll be something along the lines. Okay, delete this. This is like, is it really GG? Okay. What does that stand for? It's the composition of morphisms, and it's called GG. Huh. Okay, so I copy V1 into V3 and V2. Then I delete V3. It shouldn't be 0, it should be delete. There should be a delete here. And I think it should be V2. I think it should be like V2, there should be a delete. And now I just have to make sure I've gotten the like order right. So it should be, all in all, it should be from V1 to V2. Yeah, I believe that it's going to be hum instead of inverse. That seems like the dual. Oh, I see I have a chat. Hey, Chandu16. How's it going? Yeah, I'm trying to work. Let's see. I'm trying to work this out. Possibly if I blindly switch this. So let's do well, it's a bit happier now than it used to be. Well, it should presumably be what was it before? presumably be like v2, huh? Yes. Okay, cool. Got it. Yes! Okay, excellent. Wonderful. This seems right. Okay, I'm just going to double check the work here because this was heavily AI generated, and so therefore there's a strong possibility that it's incorrect. First thing I do, I copy v1 into v3 and v2. Then I delete v3, that operation being carried out in parallel in whisker to v2. Then I do the left unitor v2 to delete the unneeded identity guy. What is the identity? What is the name? What is the name for this 1 underscore tensor to delete the tensor unit? Yes. Now the AI will get it all right on the first try. Copy delete. So close. Copy delete v1, v2, v3. So now we're doing this equality, this other equality. The final arrow I want goes from v1 to v2. Yeah, the final arrow I want goes to v1 to v2. On the left-hand side, which I'm probably going to invert the sides here. The left-hand side. Okay, I'm going to invert the left-hand side and the right-hand side. The left-hand side, I want to get this composing 2 arrows. The first arrow goes from v1 to v2 tensor v3. Yes. The second arrow is v2 tensor v3 to v2. The v3 is going to be delete here. So now I want to use the right unitor. Yes. The first arrow will do the copy of v1 into v2 and v3. Yes. The second arrow will go from v2 v3 to v2 tensor 1. Yeah, by the whiskered delete. Yes. The right unitor will then give me the arrow from v2 1 to v2. On the right-hand side, I just want to have a carry forward arrow. Correct. So I copy v1 into v2 and v3. Then, now I want to delete v3. So the whisker, it's a left whisker and the right whisker. So I think it should be delete v3, v2, and then it should be this whisker. I want to delete v3, keeping v2 the same. Yes. Okay. All right. Copilot almost got it. It was very close, but I think this is correct. And then it's the right unitor, and it's hom instead of inv because it's being done at the end. Yes. Glorious. Okay, so I had done these two after skipping this one. So now it's going to do copy a sock. Not quite. Copy a sock. XOR a sock. So I'm gonna type in copy a sock. That's not quite it. I think there's going to have to be 6 like before, right? There's going to have to be 6. There's going to have to be 6. V5, V6. V5, V6, just like copy a sock. Final arrow I want to get. XOR a sock. Okay, I'm gonna let me do the following operation. The AI will probably understand things better if I bring things into closer context. The AI. All you have to do is bring the code you want next to it. That's not the final arrow I want. Okay. Final arrow I wanted here was that. Final arrow I want here is v1 goes to v underscore 2 aux v3 v4. Okay, now like, you know, just keep typing more things for the AI. I want to get this by composing two arrows. The first arrow is V1 goes to V5, V3, no, there should only be two things here. What I want the first arrow to do is V2, V5. Sorry. It should be V2 tensor V5. Yeah, that's right. V2 tensor V5. V1 goes to V2 tensor V5 because I come in here, right? So it's V2, V3, it's V1, V2, V3, V4, V1, V2, V3, V4. And the middle arrow is V5 here, and the middle arrow is V6 here. So V1 goes to V2, V5. V1 goes to V2, V5. That makes sense. Now it's going to say the second arrow, which is V2, V5 to V2, V3, V4. Yes. And now I have to be careful, yes. And now it's like a question of doing the tensoring, the whiskering, right? Composing two arrows. On the right-hand side, the first arrow will go from V1. This is not quite right. It's going to go from V1 to, on the right-hand side, it should go from V1 to V6, V3. No, from V1 to V6, V4. It should be V6, V4. Because it's V6, V4. First arrow is this. The second arrow is V6, V4 to the output. But this doesn't match, probably there's another associativity failure, and I'm going to have to use the associator again. Yes. Therefore, I need to use the monoidal associator. Yes. The associator gives me this arrow. The associator gives me the arrow. That's not the arrow it gives me. What arrow does it give me? It gives me the arrow V2, V3, V4 to, yes, that's the arrow it gives me. No. This is, again, it gets it wrong. It's like this. This is the arrow it gives me. The associator gives me that arrow. And the point is that I compose this, yes. Right, the right-hand side. Okay, so yes, like recalling the lesson that I learned all the way back up here, in here, the point is that it associates the aux operator associates on the right. The aux operator associates on the right. So the left-hand side, I will get this, and then V5 is going to V3, V4. So that is correctly written. But the V1 goes to V6, V4, and V6, V4 goes to V2, V3, V4. So this should look like this. And that is what doesn't match the associativity. That is what I'm going to need. The associator is going to give me the arrow that goes this way. I wonder if it's going to be like, I had to use the inverse of the associator before. Then I can compose. With that. Time to start writing. Copy. Doing lots of copying. Okay. So now we have to carefully look at what is happening. There should be whiskers somewhere. So the first thing I do is I copy, yes, so I'm over here, v1, v2, v3, v4, v5. I copy v1 into v2 and v5. And then I copy, yes, so I think now the whisker should be on this one. I copy v5. What happens now is I should be copying v5 into v3, v4. v5 is copied into v3 and then v4. But the v5 being copied into v3, v4 is itself whiskered. What is the whisker notation? Left-hand whiskered onto v1, I believe. v_1. Wait, no. v2 is what it's whiskered onto. v2, yes. And I claim there is no associator in the first one. That whole thing should have type v1, v3. What's the type? Okay, the type expected, and then, okay, but it's not, so this should now go at the end. The AI is close, but it should be going at the end. What should be happening now is that v1, okay, this is now this side. v1 goes to v6, v4. Okay, that's right. I don't think there's a whisker here, though. The whisker is v6. It should be v2, v3, v_2, v_3. And the whisker should be whiskering the v4 on. v4. Yeah. But now, what's the GG? GG. Now I need the associator. And it's probably going to be this .hom. Yes. Okay, excellent. Okay, sweet. Okay. That is good. Copy association. So we've got this whole top row now. Got the whole top row. I'm almost out of water. Okay. What next? Next, we have this, which is, I would say, the commutativity. This is the commutativity. Okay, well, we're doing a lot of operations here, but we're doing the commutativity of copying and XORing. Right, we can copy and then XOR, or we can XOR and then we can copy. So the name of this lemma is okay, so on the left-hand side here, we are copying first and then multiplying. So let's call it that. Okay, we're going to need a lot of, I sense the need for lots of wires here. Okay, so 2 input wires v1, v2, 2 output wires v3, v4, and then v5, v6, v7, v8, v9. I think we need 9 V's. Woo! All right. V5, V6, V7, V8, V9. This is the most wires we'll ever need, though. Okay. Okay. We're getting there. We're getting there. We have 9 wires. Yeah, 4 input output wires, 4 wires on the left, 4 intermediate wires on the left, and 1 intermediate wire on the right. Yes, yes. It's interesting that it's equality. Equality. The equality relation is just normal. Huh. I wonder if I'm like screwing myself here, and this isn't. It's either like there's a chance that this is supposed to not be equality or something. Okay, so yeah, I'm not gonna like, not even going to give the attempt for like, what do we want? Let's v3, v1, v2 is going to here v3, v4. On the left-hand side, we are doing a few operations. I'm realizing that there's a little bit of a weird thing here, which is that the question is, in which order do I apply? Right, because I can think of, this left-hand side here, I can think of it a few ways. I can think of it as like, first I copy this, then I copy this, then I multiply this, then I multiply this. Or I can think of it as like, first I copy this, then I copy this, then I multiply this, then I multiply this. Or I can, I can do the copies in either order, and I can do the multiplies in either order, which makes the whole thing very complicated. Huh. Is there some? I'm reminded of something here, which is this sliding thing, right? Slide processes along wires. AB is equal to BA. It seems like there's some sort of like general principle here that I should be capturing. Let me go to the definition again. Tensor hom. I feel like what is about to happen is like a tensor hom. Like the best way of describing this, yeah, the whiskers are in a certain order here. Whiskers first on the right and then on the left. But this is, I feel like I even said all this, like when I was reading, is like, what happens if I want a whisker on the left first and then on the right? But I'm sensing that the right thing to do is to write this in terms of tensor hom. Tensor hom. Because I'm also beginning to sense the need for braided categories a little bit, because sensing the need for braided categories because these two guys, they come in and they get copied, and now we have 4 outputs, right? So let's say these two guys come in as v1, v2, v1 tensor v2 comes in, right? After I have done the tensor hom, right, I will have v5, v6, v7, v8. But the inputs to the next layer have to not be v5, v6, v7, v8. They have to be v5, v7, v6, v8. Therefore, and lots of like weird associativity to happen. Because, I'll have v5, v6, v7, v8, and that will be like the associativity of that will be something like Okay, I mean, gosh, it'll start out as v5, v6 together and v7, v8 together. And I will need to then convert that to v5 separately from v6, v7 together, then v8. Then I will have to switch the v6 and the v7. And then I will have v5, v7, v6 together, v8. And then I will have to switch that to v5 and v7 together, v6 and v8 together. And only then will I be able to apply, again, tensor Hom, this time with the XOR operations. So lots of things about to go down. Lots of things about to go down. Yes. This is like the final boss. Maybe I should do the inverse and the randomness first. Inverse and randomness look a lot easier. Yeah, what it like? How am I even gonna represent this? Maybe I should do those first. Yeah, I'm beginning to think that the right course of action is to do this one last, because at the same time, this one seems like the hardest, like the longest to write, but also I feel maybe the most confident that I can eventually write this correctly. Whereas these ones, I need to figure out a little bit more about how I am handling the gap. How do I handle the gap? Is it another like pass forward thing? Is it? Let's try and figure it out. Let's try and figure out the inverse. Okay. We have to make an inverse box. That's what we have to do. We have to make an inverse box. I'm noticing that there's no like inverse equals identity, which I guess is not needed by this proof down below, but that's sort of funny. Presumably that should be another law. Okay, I need to go up. It has to have the same type as carry forward. I think what I want is inverse. Like, alternatively, another way I could do this is just to yeah, interesting. Starting to think about if, like, this is sort of an interesting observation, right? So what all of this is written for a group. All of this is written for a group where the inverse of an element is not necessarily the same as the element itself. Like you have an element and you can take the inverse of that element. Now, if we were talking about the group XOR, every element would be its own inverse. If we're talking about that sort of group, every element would be its own inverse, and we could simplify. We could simplify this. So this is done in the full generality of a group, but I can maybe like simplify it. If I want to assume that I'm specifically talking about the type of group where it's an XOR, I could eliminate the concept of inverse, and I could redraw this, right? I could redraw this. Let me yeah. Yeah, I guess that's what they call this. Is this actually visible? Is this one? I could just write right? I've just redrawn that diagram, right? I've just redrawn this diagram here, but without the I. Like, I'm just saying that the I is the same as just passing forward. And like, if I have a circle, I just delete the circle, basically. And it becomes a deletion and a 0. So, yeah. So, am I confident that this will not harm me? I think I'm fairly confident in that. Let me like try. Let me like cowboy changing the proof, but yeah, this is definitely a possibility. Let's try this. Let me try that. Let me try it. So let me comment this out for now, because that's the final boss. We're going to come back to that. Hello, let's start a new one. This one is going to be XOR self. Let's call it XOR self. We have, okay, let's think about it. We have two input. We have V1 input, V2 output. And we have two internal wires. So V1, V2, V3, V4. V_3, V_4. The final arrow I want, like in every case, it's an arrow from the inputs to the outputs. So the arrow that I want at the end is V1 to V2. On the left-hand side, I want to get this by composing the two arrows. The first one is going to be V1 is a copy, right? On the left-hand side, the first one is going to be a copy of V1 to V3, V4. The second arrow will go from V3, V4 to V2. And I don't think that there's much, I don't think there's any like additional problems there. On the right-hand side, I want to compose. Okay, this is where I'm like solving my problem by just writing. The first arrow is V1 to unit, because there's nothing in the middle, right? There's nothing in the middle. It's simply the unit. Where do I find the unit? Copy the unit. It got the size of the arrow wrong. That's weird. I don't know why. Why is it getting the size of the arrow wrong? Copy that arrow. What the heck? Why is the arrow of a different size? It's, am I going insane? The arrow below is larger. Huh. Arrow below is larger. C. What? Okay, well, that's a little weird. I don't know why the arrow is larger down there. Okay, let me start writing. I want, at the end of the day, an arrow from V1 to V2. The first, this is a composition of two things. First thing is a copy. What I want is copy. I want to copy V_1 into V_3, V_4. GG. XOR. Then I want to XOR V3, V4, V2. Cool. And now I just want to do composition of delete and 0, right? So I want to do 0 that out, and then I want to sorry, I want to delete first. Delete the V1 and then 0 out on V2. And that is it. And I noticed something here. Like XOR, I have these things, but I control the order in which I provide things to them. Do I have to use a braided category? I guess I still do have to use a braided category because I do need to exchange them. The point is I need to exchange them. Yeah, I need to be able to exchange them. I guess I see why they call it a braided category, because you have all these lines moving forward in time, and you have to move the lines back and forth over each other one at a time. What a pain. Yes, but this is XOR self. Okay, well, we've got XOR self. Here, let me refill my water. All right. Yes. Well, it's like, it's just a type class, right? If I go to, it's getting to be a long monoidal category, so I just have to add braided category there probably. Okay. These ones. So I need a randomness. I need a randomness with the same type as 0. And now I'm going to need, so this is what happens when you XOR something with randomness. So it's rand XOR. Four sounds about right. 1, 2, no, it's actually just 3. Yeah, it's actually just 3. There's V1, V2, and V3. It should just be 3. The final arrow I want is V1 to V2, correct. On the left-hand side, I want to get this by composing 2 arrows. The first arrow goes from V1 to V3, V1. The second arrow is V3, V1 to V2. but the v3 is coming from a rand here. So I need to use the left unitor. Is it the left unitor? Wait. The left unitor puts a 1 on that side, yeah. Okay, let's see if I can just write this without writing a like super long comment. The first thing I do is the left unitor guy. Just as with the mul 0, the XOR 0. It should look like the XOR 0. 0 XOR. It should look like it's rand XOR. It should look like 0 XOR. I'm just going to copy this, paste it down here. Okay, the only difference is that instead of 0, I'm doing a rand. And instead of carrying forward, I'm doing something else. I'm not carrying forward. What I'm doing is I'm deleting and then randing. So it should look like this, except that I'm deleting v1 and then I'm randing v2. Yeah. I think that's right. AI might be good enough to figure this out. Should be XOR rand. XOR rand. v1, v2, v3. Final arrow v1, v2. First arrow should be v1 to v1, v3. Yes. Use the right unitor. Yeah. Delete. I want to, no, yeah, so it's all right, except that it should be delete. Again, it should be delete and rand because it's the exact same thing. Yeah, okay. That's the XOR rand. Okay. We are building our way. We are building our way to a string diagram. Yeah, we haven't even like put the thing in the after the colon, which is going to be this bad boy. Yeah, the thing after the colon is going to be I'm still a little disturbed. I'm still a little disturbed that I have to create all these variables for the intermediate values of the wire. I'm a little scared that I'm doing something wrong there. Does he create a bunch of it? For the Yang Baxter. Like, there's a bunch of underscores, but all the underscores have values. I'm just able to figure out what all the values are supposed to be. Nothing selected. String diagram. And yeah, so this is, it's gone with this R here. And the point is that this R is actually probably what you would need for a braided category now. Braid. I see the word braid. A unital associative algebra. Braid. Let me go again to Moogle. Let me go to Moogle. No, not that. This. It was called braided category. braided category. This. It had, the point was that it had x, y, and yx. Equipped with the braiding isomorphism beta underscore. v1 tensor v2 to v2 tensor v1. Braiding. Tensor xy, tensor yx. Yeah, looks right for any v1 and v2. I guess the point is a little different. Yang Baxter doesn't insist that it's invertible arrow. Doesn't insist that it's Yeah. We should just copy and paste that. Yeah, maybe not to bother with okay, this is what we need to do next, right? Let's go for it. R for reverse, presumably. Copy. And we'll put it at the beginning to denote that it's not of this world. I wonder what operations. I feel like we're going to be surprised by needing like additional operations. Someone after I'm finished with this, someone's going to be like, "Oh, like you didn't know that you could use all these axioms from the braided category to do exactly this," but I guess it's fine. Yeah. So that's R. So let's try 9. The final arrow I want. Let's try and make this happen. We're up here. We're doing this, the final boss. The first thing the final arrow I want is v1 tensor v2 goes to v3 tensor v4. The first thing I will do, I mentioned this before, is tensor hom. What is the notation for tensor hom? Is there any notation for it? Tensor hom. Okay. Very confusing because it's exactly the same notation as for tensoring of objects, but am I wrong here? It's OX. It's \OX. Like for here, tensor obj is OX or O times. And here, tensor hom is OX or O times. Wait, where's that notation defined? Go to definition. Tensor hom. Yes, okay, there's two, yeah, it's defined as notation twice. OX or O times, OX or O times, tensor hom, and tensor ob. That's exactly the same notation for both of them. Cool. Yes. The final arrow I want is that. v1, v2, v3, v4, v5, v6, v7, v8. The first arrow, let me start like yeah. I mean, if I do this, the AI won't help me, but probably that's for the best. The first thing I want to do, I'm going to do a bunch of maybe even better to do this. So the first thing I want to do is a tensor hom of two things. The first thing I want to do is copy. I want to copy v1 into v1, v2, v3, v4, v5, v6. I copy v1 into v5 and v6. That will be tensored with the copying of v2 into v7, v8. Cool, you got it. What I would like to do, so I'm going to surround these here. This will now be composed with another morphism. Okay, so that is that morphism. Now, what I need is a morphism from v5, v6, v7, v8, v6, v7, v5, v8. Okay, well, it's got the order a little bit wrong here, but it's close. It should be v5. I think what I want here is v5, v7, v6, v8. And I also want it to be associated the same into like two separate subgroups. I don't want to end here. We're GGing again. And now we're doing the XORing. The XORing. We're doing the XORing now. So we are going to now XOR v5, v7 into v3, and v6, v8 into... Okay, that's impressive. It got it right. Of course, it didn't get that right, but... Okay, that's not right. That's not right. Blue. Surround this. Let's like heavily type annotate here. This is going to be v5, v7, v6, v8, v3, v4. Sorry, I need to like delete this side thing. Has type unit. What? Okay. I'm doing lots of like parenthesis surrounding here. I don't think it's strictly necessary. Okay, so this one no groups here. Has type. Is it complaining here? Does it know that this is tensor hom? Yeah. v5, v6, v7, v8 into v5, v7, v6, v8. Where I want, yeah. Okay. So what's it complaining about here? Type mismatch. I think it's complaining about this. I think it's complaining that I haven't done my job in the middle. The error is on this one, but I think it's complaining about this one. v1, v2, v3, v4, v6. What? Yeah, okay. Unit is expected to have v1, v2, v3, v4. Yeah. Type mismatch has type unit. Yeah, okay. Like if I write sorry here. It's a little disconcerting. I can't just write like sorry and have it be happy with me. Am I getting the like I copy v1 and v2 into v5, v6, and v7, v8. I tensor hom them. Yes. Copy. Yeah, copy is an arrow from copy v1, v2, v3 is an arrow from v1 to v2, v3. So I have an arrow from v1 to v5, v6. I feel I've gotten this right. I even enclose in parentheses to make sure that it's not like, is this the problem? No. I don't understand what it's saying is unit. Type mismatch unit. Where have you, presumably here. What happens if I, okay, maybe I'll just try and do the middle one because I have to do the middle one anyway, and then I'll see if it continues to complain. Maybe the problem, okay, the problem, no, the problem is this. This is a little dumb. It's a little dumb indeed. See, the thing that I would like to complain about is that, like, when I have written this, it is complaining with a red arrow under this part. It's like, you can even sort of tell that this is a dumb error message because the thing it is highlighting in red is not like, it highlights the close of this parenthesis, but it does not, like, this pink parenthesis corresponds to this pink parenthesis. So the fact that it red underlines this pink parenthesis and it doesn't go all the way to this other one should be like a clue that something is wrong. Maybe the issue is that yeah. Sorry. Okay. So the point is that this should be composed of a bunch of like associators and the braid. Braids and associators. Yes. Yes, and it even tells me what it should be. It even tells me what it should be. See, this is where I would like to say, like, by Aesop. This is where I, like, am sneakingly suspicious that if I were to just Aesop, I'm like, can I do that? It's gonna blow my mind if I can. By Aesop cat. By Aesop. What does it imply? Oh, it's just telling me to, what? Apply carry forward. What? No, that can't be right. No, I see the issue. The issue is that it's finding carry forward, and carry forward allows you to like go make an arrow from any category to from any object to any other object, and therefore it is not working. Is there any way to hide? I see the issue. I see the issue. Seems like an appropriate question for the good people in the Lean forum. What I want to ask, category theory people. Okay, seems like a good time. To am I signed in to Zapier? Log in. The issue is I don't know what my usual login credentials are. Just a moment. Can I like hide my screen for a moment? Yes, that seems to be hidden. Wonderful. Let me figure out. Do I log in with Google? Maybe? Yeah, that seems to have worked. Yeah. Okay, I will. Quickly log in here. Okay. Sweet. I am now logged in. Enable notifications. Allow. Cool. I can now turn the screen back on. I'm logged in. This is how, okay. Yes. Time to ask a question. Asking a question. Yes. What I want to figure out is how to do this, how to achieve this goal, without like automatically. Please prove this for me automatically. Please prove this. Yes. So, did I like Aesop cat is something that I've also heard of. Okay, but if like Aesop cat question mark, again, it's just doing carry forward. So is there a way of hiding something from Aesop? Is there a way of hiding Aesop? I mean, I guess the point, let me look at this. The point is that I should just, I'm in tactic mode, right? So I can at least do clear carry forward, clear carry forward. Clear everybody. Delete, copy, yeah. Paste, clear everything. Copy, delete. Carry forward, copy a sock. I'm deleting everything. Sock. I mean, in theory, I can just delete this whole thing, make it the very first thing I prove, which is a little bit of a dumb solution, but clear, carry, forward. What does Aesop say now? What are you doing? Apply XOR. That's not what I want you to do either. I don't want you, so yeah, so it's applying XOR because it is in this situation and it sees that XOR will literally take any tensor product and produce another value. Okay, let's clear copy and XOR. Okay, great. ASOP fails. ASOP cat. Failed to prove the goal after exhaustive search. It really feels like there should be like a tactic. The thing is, it's the sort of thing where it's like, yeah, it's interesting. It's interesting. Okay. How do I even ask this question? Okay, usually they want like a minimal working error. Yeah. I think when I do, okay. Select all. The thing is, I wish I could. I wish I could. Okay, where should I ask this question? Should I ask this in the string diagrams? Let's ask this question. Hello. I am currently live streaming my attempt at the diagrammatic proof of the cryptographic of the OTP from the paper I linked. I have come to the following goal. Maybe, okay, maybe the point, maybe what I should simply do. I don't need delete or 0 or rand here. Following. Is there a tactic that what I want to ask is there a tactic that solves this kind of category-theoretic goal? Question mark? The thing is, wait, what? Yeah. I want to do this in the obvious way. Lots of associativity using R to switch the V6 and the V7 with lots of associativity associativity on either side. Okay, we don't actually have to say hello. That's super dumb. Gotta get people into the live stream, you know? I'm gotta advertise my live stream. Okay, but the real issue with this entire idea is that probably no one is online right now. Are people online? Maybe a few. I don't see any people from this thread online, not necessarily. Okay, so can't necessarily count on people responding to this. So I guess we should just try to prove it ourselves, right? Should we try to be proving it in the by notation? Okay, we can always do show term at the end, right? Yeah, no, it was too much to hope. It was like, wow, we've got AI wanting to solve it for us. Okay, what is the status? The status, okay. I outlined the plan for this before, right? The point is, but the thing is, there's like, oh, we have to associate with whiskers on you, like every time we associate. It's like, like every time we associate, there's going to be a whole bunch of whiskers everywhere. Guess we can think it through. The tactic that uses the attribute reassoc. Okay. Reassoc. Okay, that's fine. We can look it up. We can look it up in Nice React. Lean for tactics. No, this is not what I want. I have, let me pull up. There's this website with all of the tactics. Yes, so let's see. Act change. It could be act change. Could be act change. Seems possible. How do I use act change? Convert to G using N. Okay, how do I use act change here? The point is I want to change. It's even a little weird though, because it's like this arrow, right? I want to change act change AB plus CD plus EF plus G is less than N. Act change A plus D. Okay. Associative and commutative. It looks like both association and commutativity are being applied here. I wonder if I need the braided category for that. Let's see if there's any more wisdom here. Act change. So I guess this is not, so I need to say what I'm doing. So the point is that I have V5, I have this type. And I think what I'm saying is that I want to go from that type to this type. Ooh, if this works, that'll be mind-blowing. What I want to do is this. I mean, I want to change this anyway. Okay, well, I've changed it, but I have, like, the goals are, like, it hasn't automatically. I mean, I think what's happening is that I've just called change, essentially. So, like, change. Oh, well, actually, no, change doesn't work. Act change. Okay, well, what is act change asking me to prove? It's asking me to prove that V5, V6, V7, V8 is equal to V5, V6, V7, V8. Which I can certainly do by associativity. And then I have to prove that V5, V7, V6, V8 is V5, V7, V6, V8, which I can do by associativity. And then finally, I have to show that V5, V6, V7, V8 is equal to V5, V7, V6, V8, which of course requires the commutativity. So, why do, like, what act change? Convert to is act change using. Act change using. Act change using n is convert to. What is convert to? Learning more about tactics. Convert to. Cases, choose, C, G, convert. Where is convert to? Convert to. Convert to G using N attempts to change the current goal to G, but unlike change, it will generate equality proof obligations using conger to resolve discrepancies. Convert to G defaults to using conger exclam1. Convert to is similar to convert, but convert to takes a type, while convert takes a proof term. Convert to G using N. using conquer exclaim n to resolve discrepancies. Convert to, same as convert. What is convert? Convert. Maybe I should just be trying convert. Okay, well, that's not what I wanted. Convert to? I mean, I guess the point is, like, it makes sense that the v5 isn't disappearing because that is not like an equality. It's more of a whiskering operation. And so I basically need to like demonstrate. Does this thread help? Rewrite a sock is not ported. Okay, this thread looks like it will help. Okay. Rewrite a sock isn't ported to lean for yet, but I guess I would need simple sock for lemmas like this. Rewrite a sock is not ported yet. A, B, B, C, A, D, D, E, C, E. A, B, B, C, C, E is A, D, D, E. My actual use case, I wasn't even using category theory. Everything was R linear. Do we have tags in my soul? I know you said you weren't using category, but for category theory, there's a conv mode slice tactic for reassociating. Whoa, is my mind about to be blown here? What is conv mode slice tactic? A conv mode? Bro, I don't want to use conv mode though. Oh no! Okay. Okay. Conv mode slice tactic. Okay, well, thank you, Kevin, for your idea. TLDR slice. Slice. It's just, okay, slice. What is slice? Slice. Is that mentioned in the category theory library? Slice. In the tactics, element of P, Q, R, S for slice. IJKL. Sleep. Slice. Zooms to the left-hand side. Uses associativity for categorical composition as needed. Slice. LHS. Yeah, that might work. Okay. I'm proving things equal. Yeah, so now that I've done the convert to, I'm proving things equal. I'm a little, wait, why is it, why is it that when I focus the goal, it doesn't seem to work anymore? I focus the goal and suddenly the thing that I'm supposed to be doing is gone. I'm also not exactly clear on what slice is doing here. Let's view in playground. Waiting for lean server to start. This is happening. Okay. Okay, but of course it's not. We need to like import. Sorry. Let's add all of Kevin's imports to this file. Mathlab.tactic. Cool. Yes, okay, reasonable. Slice RHS zooms to the right-hand side, uses associativity for categorical composition as needed. Zooms in on the 8th through the bth morphisms and invokes tac. Zooms to the right-hand side. But why isn't it? Invokes categorical composition is needed. It invokes categorical composition is needed. I mean, that sort of makes me feel like there should be a single one-liner that dispatches this goal. The point, the trouble is it's not. The trouble is that it's not categorical composition. It's monoidal categorical tensoring. That's the issue. This seems like it is more for categorical composition than monoidal categorical tensoring. Slice. Specialize. Yeah, I suppose the top level issue is that I'm not trying to prove an equality. I'm trying to prove an arrow from one type to another. Slice. Maybe if I look at the not slice, not like slice right and slice left, but just slice. That's not an actual tactic. Yeah, okay. Solve this. Zooms to the left-hand side. Categorical competition. What is the actual syntax tomfoolery? Well, it's the syntax for the category theory. Yeah, okay. Slice is not a real thing. Yeah. Okay, maybe I should just try and do it. The thing is, I'm mildly like, why? Here I have to prove two things are equal. Is it not the case that I can just do like sorry, and then sorry again, and then sorry one more time, and like here I have the right thing? Yes, here I have the right thing. Okay, cool. We're making progress. So what to do now? What was the first thing that Yale suggested? Act change. that's how I got here, right? What happens if I... Yeah, it doesn't do. Like the associativity. In some part, I have to be like invoking the monoidal category. Okay, the OP of the thread is coming in. Okay, yeah. We can use docs MATLAB tactic coherence monoidal comp. Can you look at this syntax? What is this? Okay. Yeah, what the actual syntax font tone? Yeah, it's utterly mind blown. Mind blown. Wait, does this just do the entire thing? Monoidal comp. What's happened here? Okay, this is v5, v6, v7, v8, v5, v7, v6, v8. This is what I needed, right? Exact. This. Unexpected. Okay, I need to import something. Yeah. Coherence. I need to build another few files. What I've invoked here is some witchcraft that, yes, we just stick the tensor with the category, with the arrow composition, and it'll all work. Okay, let me try and parse out what this is possibly saying. Like v5, I have v5 over here, and I have R of v6 and v7 here. That is being, this is the whisker arrow. No goals. Blah. The string diagram widget does not support monoidal comp at the moment. So that's what's being, this is like monoidal comp or something. If I go to definition. Yeah, monoidal comp. Type as .gg. Huh. Wait, so are they telling me that I'm not going to be able to see my diagram at the end of this? That's sad. Well, I mean, in some sense, I'm like, the end is here. The end is nigh. Like, instead of the exact statement, I can just do this. Yeah, okay. Cool. That's that. Okay, I just need to finish this. And then I can consider this. String diagram widget does not support monoidal comp. String diagram widget does not support monoidal comp. It should be fine though for the sad. Okay. Yeah, the problem is there's like, I'm worried that like, yeah, there's gonna be like, I can state it. What am I doing here? Okay, nevertheless, I want to finish this. We now have to represent this. Okay, it's a composition. Okay, we're using V9. We're using V9. What are we doing? We're doing, okay, like this one will be V1, V2 to V9 to V3, V4. So what is it? It is first I XOR V1, V2, V9. Copy. Yes, that's it. And I feel like this deserves to be towards the end. All right, so that's that. That's all of the things completed. Hype. Now I simply have to write out these, like this diagram and this diagram. Remember, I is gone. So this diagram and this diagram to finish. V sub A. V sub A, yes. Yes. And presumably we don't even have to. Let me take a look at like how it looks. How does this look? V F whiskered. Yeah. So it's some things that were whiskered on. How does this, the Yang-Baxter, what happens if I, okay, let me look at the Yang-Baxter thing again. So I have V3, V2, V1. V1, V2, V3. Comes down the page. Comes down the page. Because this is V1, V2, V3. So it starts here and it goes down. Like, yeah, the unfortunate thing here is that it's going, the way that these are written, the information is going up the page. It would be a little bit more, make more sense to me if it were coming down the page. So in the Yang-Baxter, there's the 3 input wires, and there are inputs and outputs. So IR V1 V2. It's an assertion of this fact. I'm still trying to understand if the fact that this lemma is technically sorried out is a representation of the fact that this is not a true lemma, or if it's just that it's a very hard to prove lemma. So, all right, they did it without illustration of Yang-Baxter. Yeah, okay. I want to go in with A, and I want to come out with E and B. And I want to write I want to describe the whole thing. How does R look here? It's this arrow. It's just this arrow. I don't really understand. Like R is this arrow, right? Is this like R v1 v2 is an arrow which goes from v1 tensor v2 to v2 tensor v1. But what about all of my arrows that I am... This is where I don't quite understand what I've done. I have units and things coming out of units and things going into units. And the weird difference is that, like, here there's a whole bunch of wires, and here there's only like a couple wires. I guess the point, okay, so if I'm thinking of the type, right? If I'm thinking of the type, what I want to do is I want to establish an equality between two values of type arrow from VA to B tensor VE, right? Like if I XYZ, what I think I want to do is establish an equality between something I am not yet specified, which is V. Okay, first of all, I believe that we can do away with XYZ, and we're going to go with V sub A, V sub B, sub B. Does that, sorry, sub B. It doesn't actually exist. That's annoying. Fine. What I want is an arrow from VA. What is the arrow? Syntax. V. Let's try and like replicate the like left to rightness of the paper, if not the up and downness. An equality of that with something, neither of which I have yet specified. Do not know how to synthesize placeholder context. So for the output, I feel like I can maybe do it, right? The output is simply, because there's no like wires to speak of, there's no additional wires. The output is simply going to be VA. I'm going to have to cons on a unit. First up, what do I want to do? I want to cons on a unit to the left. What is that operation called? The lambda underscore operation. The unitoid or something. The left unitor. I think what I want to do is I want to first do the left unitor. The inv of the left unitor. Yeah, sorry. Let me grab it. the inv of the left unitor on VA. That gives me unit tensor VA. Just check. The left unitor is the one where the unit goes on the left. Yeah. So that produces a unit on the left. GG. And now I'm going to take rand VE and what do the other side I'm doing to do carry forward VA VB. Okay, well that at least it has the right type, right? Yeah. Do I just create a bunch of wire variables? Do I literally just create 1, 2, 3, 4, 5, 6 wire variables? I guess. Actually carry out the proof is the tricky part. You can do like rewriting. That's interesting. Okay, what happens? What happens? 6 additional of these guys. Let me just go and quickly copy 6 of them. 6 intermediate wires here in the one-time pad. And we're going to build this with our bare hands. The first thing we were going to do is the right unitor. The next thing with the right unitor after that, we must go for the rand. We must create rand. Rand, well, let's rand nothing. So, sorry, let me count the wires again. So VA, VE, VB. Then we have V1, V2, V3, V4, V5, V6. So we want the rand on V1. That's a little confusing. This is not exactly what we want. It's like we want to we want to only apply it to the right hand side. Is that what the whisker is? Let me just recall my whiskers. Whiskering is when we apply a function only on one side. Yeah. So VA, what is the LHD? What? No, why LHD? rand v1 yeah, so we're just, what have we done? We've gone from VA to VA tensor unit to now VA tensor rand v1. Now we are going to have to operate on rand v1 again. So now we are going from, so again it's VA whiskered, but now it will have to be the copying, right? So we are now copying v1 into v1, v2, v3, v1, v2, v3. v3. Okay, so now we have VA tensor v2, v3. Now we must do an associative action. Now we must associate. How do we associate him? Yes, so we want to go A something inverse. We want to do the inverse. Where is a good example of that in my previous code? I've written this. I believe what we want to do now is this. VG. Okay, so now we've reassociated it. And now we have VA V2. So now we're here, and we have VA V2 together, and then tensor with V3. So now what we must do is on the yes, now we can do it. Now we can do both of these two things at once using the like tensor hom. So what we want to do now, the VA and the V2, they need to become, the VA and the V2 need to become V3 via a XOR. No. This is, no, yes. Yes, this is an XOR operation. So XOR VA V2 into V3. Right, okay, so recalling my little operation from before, I was going to say that I'm ignoring the inverse. Inverse, I'm just passing forward. So this is now getting whiskered onto this is V1, V2, V3. I didn't get this right. It should be V4. This is V4. So we're XORing VA and V2 into V4. And this is getting whiskered onto V_3. What happens next is, so now we are here. We have V2. We simply have V4 tensor V3 here. I didn't count the number. I didn't count things right, because these two are part of the same. V1, V2, V3, V4, V5. There should only be 5. Let me correct that. Because of this like inverse eliminating, I eliminated the XOR inverse from the math. So, just to refresh, we reassociated, at which point we had VA and V2 together, and then V3. The V2 and the VA and the V2 became a V4 via the XOR operation. So now we have V4 XOR, we have V4 tensor V3. The operation that needs to be done now is the V4 needs to be copied out. So copy V4 now into, on the left, VE, and on the right, V5. That is again whiskered onto v3 because v3 is on the side. Now we must reassociate again. So we need the associator to go in the forward direction this time. So this is hum. Hum is the command. Great. So now we have VE tensored with V5, V3, and now simply we have VE over here, and the V5 and the V3 need to be XORed finish. Yeah, needs to be 3 of them. Yeah, and it can infer, in fact, the types, but let's just, yeah, it says V5, V3 into VB. So let's just write it on out for completeness. V underscore 3. This is going to be V underscore B. No, or capital B, V capital B, whatever. Cool. Bye, sorry. So now let's see if we can get a, yeah. All these intermediate wires. Let's see what happens. Can I like shift click? String diagram. I don't know if I've quite achieved that. I feel like I'm a little bit worried that it like is freezing on me. A little bit worried it's freezing. I'm definitely shift clicking, right? I do. Let me scroll back up. Make sure I'm like practice my motions. I'm here. I have this like whole equality that I want to. I go here and I shift click and it appears. Yes. Yes. I shift click and then it appears. Great. Yes. But what I want is to be able to simply shift click here. I wonder if could the associators be screwing it up? Shift click. Okay. I don't know exactly what I've done wrong here. Ooh, no. Should be able to capture the I wonder if I can I like shift click something else? Can I try this? Okay. what they're telling me here is not related to my problem. I want to know why shift clicking isn't fucking working. The whole point of this was to like, does this shift click work? Why doesn't it? The point, maybe the issue is that I haven't, the issue is maybe that I haven't engaged, maybe the issue is that I haven't engaged anything. Like, so I do this, w.lim, because I need to like have my false ready, false at hand. Yeah. I'm suddenly hopeful again that I will be able to accomplish my goals. So false, exact false lim, exact. No goals, yes, my goal, my one goal here is this. Shift click. Woo! Look at that! Look at that! Oh, that's so friggin' cool! That's so cool. That's so cool! Ah! Yes! Oh, that's so cool. Okay, I got it to work. I got it to work. I need to tell him. That's so cool. All right, we gotta make our screenshot. That's so cool. Okay, I think in theory, I literally did not have to do any of the work to, I didn't actually have to do any of this work. Right, so it's called, yeah, like, one thing to note is that it's upside down reversed from what we see in the paper, because we're coming from the top. So VA comes down to VA and the randomness generation. VA, the random generation, gets copied into V2 and V3, then it gets XORed. Then, yeah, now V3 is traveling along the outside. Then, after the XOR is copied, and we move into here, and then VE and VB. Right, the point is that I should start to be able to rewrite things. So, like, copy XOR com is the, like, what happens if I rewrite? Copy XOR com. Did not find instance of the pattern. Yes. Yes, of course you didn't find instance of the pattern because we are undergoing a massive, like copy XOR com, right? Like, but what are all the, like, wires? The thing is, I haven't, like, told you what wires to make for it. That's sort of interesting. I wonder how that's supposed to be done. Like, if I had if I, like, provided a whole bunch of other wires in the argument, maybe I can, like, introduce those wires here and say, like, copy XOR com into, like, these wires. And then I would be able to, because the copy XOR com is when I have, okay, well, maybe the problem is I need to do it in the reverse direction, actually. No, it still doesn't work. But, like, the point is, I I have this XOR copy here. And what I would like to do really is to isolate the XOR copy so that I can rewrite with it. Yeah, that's cool. How long have I been? Yeah, I spent 4 hours on this, and I didn't technically need to like do any of those. On the like. Okay, can I see? Here's the question. Here's the question. Can I see the like the individual like manipulations if I am the thing is I simply declare them. I don't well, if I go for instance here, can I shift click this? Ooh, I can see more. Okay, well that's the one that's sort of garbo because it's like the it's got the like special like things that it doesn't understand. But if let me try. What if I try this one? And I can like go on all of them, right? I can like, let's see, like what's a good one? Well, the good one is the super complicated one, but I can do like the associativity one. Or I can do the like the XOR self one. That's a good one. XOR self one. I mean, what I should really do is I should yeah, I should do this. Wonderful. Right, now it's time to let me just commit this so that I don't lose track of it. Yes, what to do. What I want to do now is create a new branch called branch will be Bolton Bailey time pad string diagram enter save. Of course it deleted it because I'm dumb. Yes, but it does this. And let me commit this to draft of theorem. Commit. Publish branch. All right, now I can go and go to my GitHub or something. I'll leave that on. Okay, it depends on, this is a dependent PR on that other PR, of course. What is the name of that other PR? I feel like I was given, yeah, 10.581. Edit this. Yes, very good. The style is not good. Category theory. Excellent. Okay, this is very cool. You know, I could try and go and complete the proof, but that would be very that would be, you know, something in itself. Maybe I'll do that at some point in the future. All right, very cool. All right.